Let it start.
Oh. Other guys are off tomorrow today.
Yeah, Venkat is not available.
Okay.
So Silva sir will be here like at 3:30.
Okay.
So the thing which we are going to discuss today is TRV,
Yes.
transient recovery voltage, and what is the theory behind it, and the basic theory, and how to model it in PSK. That's what we are going to see today, and
Okay.
what are the cases to be derived in TRV.
Yes.
So basically, first 2 hours I will take care of it. So I will explain you what is the basic theory, very basic theory, and how to model it in PSCAD.
Okay.
And there's another update in 5 also, like in 4.6 and 5 there is an update in TRE, like we can see that as well, like how to model it in latest version,
Okay.
to some extent, because I'm also new to that. I have done it, but I'm just new to that, like just now I have seen it, so we can discuss that
Okay.
as well, how to model it in 5, like version 5.
Okay.
But I'll show you how to model it in 4.4.
Okay.
Yeah, sorry, 4.5, and like there are some different things in our modeling, so that we are going to discuss today.
Okay.
So do you have any doubts on last class ferro resonance?
No doubt on ferro resonance. However, I have one two question on that. Another one. Uh,
VFA.
yes, of course.
Okay.
Yeah.
Fine. So we can start with TRV. So let me
Okay.
share my screen, and I'll
Okay.
just give you some basic details on that.
Yes, please.
So can you see my screen?
Yes.
Yeah. So this is IEEE standard for the break, for generally for TRV
Okay.
above 1000 watt, like 1 kV. IEEE
Yes.
C37. So that is the
Okay.
standard.
Okay.
So this is the standard for this IEEE standard, and this is IEC standard 62271 part 100. So
Okay. This
this
is
IEC 62271 part 100. Like after part 100, it talks about circuit breakers.
okay.
Fine. So I just want to go through this IEC standard, not the all pages, like
Okay.
just first
Yes. Yes.
10 or 20 pages, so that because why I choose IEEE, because it will be easily understandable for us.
Yes.
But
Yes.
IEC, that they will like use some other language, we like I can't understand that. I have to like read it for more than 5 or 6 times. But IEEE is just like that.
Yes.
You
Yes.
can
Yes.
just read it.
Yes. I triple
So
is
that's
simple.
why, yeah. So that's why I choose IEEE. Fine. I'll just I have highlighted the important points over here so that it will be easy to just.
Okay.
So,
Okay.
so general thing, like what is transient recovery voltage? The transient recovery voltage is the voltage that appears across the terminal of a pole of a circuit breaker after interruption.
Yes.
But before just talking about this, do you have any idea on TRV? What is transient recovery voltage? Have you heard it, or have you
Yes.
come
Yes.
across that TRV?
Yes. I watched this PSCAD webinar again last year
Uh,
or something. Yes.
okay.
So I am aware of the the phenomena, like after the circuit breaker opening, it will have some uh, voltage on either side of the pole,
Yeah.
and then one, it can, if it goes in higher in magnitude, it can create a ray strike.
Yes. So the same thing here. Even this is some PSCAD webinar, like that
Yes.
PPT they have used. I've just
Okay.
downloaded. So this is system one. Like let us assume this is on low source side and this is on load
Yes.
side.
Okay.
So the voltage, like between the load sides and source sides after the interruption or at the interruption of the circuit breaker is basically NTRV. The voltage between the contacts. So there will be a voltage here, which is on source side, and there will be a voltage in load side. And if there is a fault, and it's and or in there is a de-energization case, if I'm going to just like separate the contact, or just going to open the circuit breaker, there will be some voltage between the contact. So basically that is TRV, transient recovery voltage.
Yes.
So even this IEEE are trying to say that's the same thing. The recovery voltage is the voltage that appears across the terminals of a pole of a circuit breaker after interruption.
Correct.
So after interruption, there will be some voltage and across the terminal and that voltage is the TRV, and that's
Yes.
the TRV. That's our objective to find it.
Yes.
So basically, so this voltage may be considered in two successive time intervals. One during which the transient recovery voltage exists, followed by a second during which a power frequency voltage alone exists. I'll just show you the waveform for it. That would be clear. Yeah. So this waveform, right, like the rounded portion.
Yes.
So
Yes.
that is basically a TRV. So the oscillations is because of the higher frequency, and followed by the normal power frequency
Power
with 50
frequency
hertz or
voltage.
60. Yeah.
Yes.
So power frequency means it's in 50 hertz or 60 hertz based on the system frequency
Yes.
or the equipment frequency. So that is power frequency. So the same thing they are trying to explain at this point. The
Yes.
voltage may be considered in two successive time intervals, one during which is transient recovery voltage exists,
Yes.
followed by a second during which is power frequency voltage alone exists, which is 50
Yes.
hertz. In our system, we are trying to consider 50 hertz, so I'm just terming this as in 50 hertz.
Yes.
So next, the important point. This is one of the important point. The TRV is the difference in the power system response voltages on the source side and on the load side of the circuit breaker.
Yeah.
So, for example, sorry, I'll just open a paint. So if there is a source over here, and
Yes.
if there is a breaker and there is a load side, this is load side.
Yes.
So this is load side and this is source side. So mainly the voltage between this is TRV.
Yes.
So the main objective for TRV is there should be a voltage in this side and this side. So that is basically a TRV. Like the voltage, I'm going to study the TRV, which is
Yes.
the voltage on the load side and as well as the source
Source
side.
side. Yes.
Yeah. So this is TRV. This is TRV. So the nature of TRV depends on the circuit being interrupted. Primary. Okay. Then this point they're trying to say is the nature of the TRV, like the nature of the waveform, that depends on the system resistive, capacitive, and inductive.
Okay.
So how the system is predominant, like it's a resistive system or a capacitive system or inductive system, based on
Yes.
the system parameters, the nature of TRV depends on. This is an important point. Lot of people, they don't understand the system parameters, importance of system parameters. So the
Okay.
importance of system parameters is always lies, and it depends. The TRV depends on this system parameter. So based on the system parameters, your TRV waveform, you would expect your TRV waveform based on your system parameters. So next, the general thing we are going to talk about. Yeah, no, I don't want to talk about that. Yeah. So do you know what is first pole to clear factor?
Yeah,
Okay.
that basically phase towards fault clearing
Yes.
ratio of like a healthy voltage on the phase without fault, and then voltage at the time of a fault or
Yes.
something like that.
Okay. So the first pole to clear factor is like it depends on the grounded system. How the grounded system is there. Like in one of the cable data sheet, like in OHL data sheet, they used to give. Like I'll just show you that.
It is the
Uh,
ratio of voltage on healthy phase during the fault and without fault. Is that right?
yes, exactly. Like I'll just show you that. Yes. So your understanding is right. Uh, Input and 400 kV JF. Not this one. I'll just show you one of the
Yes.
breaker details. Current transformer, high speed earthing switch. The second one is breaker. This is a circuit breaker. So here they will give the what is the first pole to clear factor. Like the
Okay.
first pole to clear factor is 1.3.
Yes.
So this first pole to clear factor is basically depends on the grounded system. For the
Yes.
ungrounded system, ungrounded system or non-effective system, like if I say effectively grounded, is solid grounded, like
Solid
without
ground.
any resistance and capacitance or without any inductance, I'm going to ground my system.
Yes.
So that is a non-effective system. And for ungrounded system and non-effective system, the first fault to clear factor will be 1.5.
Yes.
And for effective grounded system, which is solidly earth system, the first fault to clear factor will be 1.3. These are typical values.
Yes.
So you can check it. You can check it in the data sheet itself. Like you can get it from the data sheet itself. Like if you check the circuit breaker data sheet, you will get this first fault to clear factor as 1.3.
Okay.
So Friday, I think so. Yeah, Saturday or Friday. Friday we have talked about that assignment, right?
Yes. 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 Yes.
Yeah. So it depends on that. Like so the first fault to clear factors depend on that. Like how the grounding is done.
Done. Yes.
So basically the KPP, which is a first fault to clear factor, plays a very important role in our TRV. So based on this, our voltage will be measured, or the
Yes.
over voltage will be referred from a table. Like we will be referring our table. So based on this value, like the table's value will change. Yeah. Again, a TRV as a two types, like the parameters will be of two types, which is a two parameter TRV, which is less than 100 kV, and a
Okay.
four parameter TRV, which is above 100 kV. Like I'll show
Okay.
you the waveform for this. This is a this is a four parameter TRV.
Yes.
Typically, it will be used after or above one after 100 kV, 100 kV. So
Yes.
for typically a two parameter TRV will be used less than 100 kV.
100
So
kV.
this is how a four parameter TRV will be, like starting from 0, then it will have a curve, and then it will have a curve, and that will have a straight line. So this is four parameter, and the two parameter will be something like this. So
Yes.
only one edge you can see,
Yes.
but in a four parameter you can see one and two edges,
Yes.
like two edges. Like this is one edge and this is another edge. So, so this IEEE I've segregated this two parameter and four parameter based on the kV. So if it's a less than 100 kV, like two parameter TRV have to be chosen. If it's more than 100 kV, then four parameter TRV have to be chosen. So
Yes.
based on the kV level. Okay, yeah. IEC have some difference on this, but I'll explain that when we are explaining IEC standards.
Okay.
So this is four parameter and this is two parameter. So we are going to talk about what is the delay line or what is this delay line. So the influence of local capacitance on the source side of the circuit breaker slows the rate of rise of voltage during the first few milliseconds of the TRV. So this rate of rise of voltage is again an important thing in TRV. We used to measure some basic things in TRV. Like first one is what is the rate of rise of voltage.
Yes.
So this is the rate of voltage. The first peak is the rate of rise of voltage. Rate of rise of recovery voltage, triple RV. The first peak is the rate of rise of recovery voltage, and that depends on the capacitance.
Capacitance on source side.
Yeah, capacitance of yeah, capacitance, basically that capacitance on the source side, exactly. So the delay time, like it's the local capacitance on the source side, which is the capacitance on the source side of the circuit breaker, slows the rate of rise of voltage during the first few microseconds of the TRV. If the
Okay.
capacitance is higher, this rate of rise of recovery voltage will be lesser.
Okay.
So it depends on the capacitance on the source side, or it depends on the capacitance before the circuit breaker.
Yes.
So the RRV is always depends on the capacitance, the capacitance on the source side. So they are trying to explain what is the delay. Like this is the delay, right? So the first peak it's an triple RV, and it depends on the capacitance of the system.
Okay.
So the next point I want to explain is next the what is UR, KPP and KF. Like while talking about the table, we will be seeing these values.
Okay.
Like UR is the rated voltage,
Yes.
like the circuit breaker's rated voltage. Here, this is not a system rated voltage. The circuit breaker's rated voltage. I'll show you that. So it will show you the rated voltage of this switchgear. So can you see the switchgear's rated voltage 420 kV?
Yes.
But the system voltage is 400 kV. Like we have to take the 400 kV.
Yes.
But look at the circuit breaker's voltage. It may be different. Rated voltage is 420.
Yes.
The system is 400, but the rated voltage is 420. I'll just show you 220 kV data sheet also. Yes, this is sitting, I think so. Yeah. This is in 220 kV. Like the system voltage is 220 kV. But look at the circuit breaker's voltage. Circuit breaker rated voltage is 300. Like the specified is 300. The offer. This is the offered value. Like we have to take the offered value. Like required an offered value. So we have to take the offered value, and that is 300 kV. But the system voltage is 220 kV.
220.
So while talking about circuit breaker, you have to take this voltage.
Rated
What is the
circuit.
rated voltage of the circuit breaker?
Circuit breaker. Yes.
Yeah, not for the switch gear or the system voltage.
Yes.
So this is the rated voltage, and this will be 300 for 220 kV. Like it depends on the circuit breaker how they are offering. Next, the first fault to clear factor. It depends on the grounding system, and you know it. You can get it from the data sheet.
Yes.
Next, the KAF is the amplitude factor. It depends on the KAF is the amplitude factor. So I'll show that what is that amplitude factor.
Okay.
So for circuit breaker in overhead line counter systems, which is OHL, the amplitude factor will be 1.54. For a circuit breaker in cable connector system, which is 1.4, and if it's an OHL and cable, then it's 1.25. So based on the transmission line or cable, my KF depends on, like if it's 1.54, then my UC, like what is UC? I'll show you what is UC. So this is UC, my maximum peak, right?
Maximum. Yes.
Which otherwise I can say this as an triple RV.
Yes.
Otherwise I can say triple RV.
Yes.
Rate of rise of recovery voltage.
Yes.
So yeah. So my UC depends on KAF, and that KAF depends on the what is the system, whether that's an OHL or cable.
Cable.
For OHL it is 1.54, which means if there is a OHL, there are chances of higher triple RV.
Triple R. Yes.
If there is a cable, then there are chances lesser than triple RV because it's 1.4. We are going to multiply it. You are not going to divide it. It's a multiplication. So it just 1.4 will be lesser than 1.54. So my triple RV, if there isn't cable, then there will be some lesser chances are there for the lesser triple RV. So similarly for OHL and cable, then the triple RV will be much lesser.
Yes.
That's 1.25.
Yes.
So I'll show you why they have why for the OHL is 1.54 and for the cable is 1.4. I'll show you that. So the RRV, now they are talking about RRV, which is UC. I can say triple RV or UC. UC is the peak value, right? So for the overhead line has a small amount of inherent capacitance.
Yes.
So since the capacitance of the OHL is lesser,
Yes.
the RRV is like higher or the increase in RRV.
Yes.
Since for the cable the amount of like the capacitance is higher when compared to OHL, so the RRV will be slower because it depends on the capacitance.
Yes.
So I'll just give you like one of the reference for this, how they are like saying, because for OHL how they are trying to say lesser capacitance.
Yes. Yes.
Like this is like 210, right? Yeah. This is one of textbook, like standard textbook, power system stability and control by Prabhagundur.
Ah,
So
it's very famous book.
yeah, this is a very famous book. Even in ME, they will recommend this book for to study this. So this is one
Very.
of the textbook.
Yes.
So if you go to page number 210, like that will be talking about transmission line. I'll just
Yes.
show you that as well.
See, Indian are publishing nice books,
Yes. So this
and
is
other are
chapter
using.
6. Yeah. So this is chapter 6, talking about AC transmission lines.
Ah,
Like if you just go into 210, page number 210. Here they will be giving a table like
yes.
typical values for OHM for 230
Yes.
kV, for 345 kV, for 500 kV, for 765 kV.
Yes.
Look at the BC, which is a capacitance value.
Yeah.
Like the capacitance value of 230 kV is 3.371.
Yeah.
This is for OHL.
OHF.
When you just come down, you can see, you can check for cable. The same thing for 230 kV is 298.8.
Yes.
So there's a drastic increase in capacitance value.
Yes.
So this is the reason why they are trying to say in a OHL the rate
Yes.
of rise, the triple RE is faster. In cable, the triple RE is slower.
Okay.
Yeah. So any doubts up to this, Himanshu?
No. No. No doubt at all.
Yeah. Fine. So basically the TRV and triple RV it dictates, or it depends on our system parameters. It
Yes.
doesn't depends on the circuit breaker. It depends on how our system is and how the system parameters plays. So it's similarly for even for ferro resonance, something like that, right? So based on the system parameters, there is a ferro
Yeah.
resonance or not, or there is
Not.
an oscillation or not. We used to say. Similarly, in TRV also, we have to model a system parameters in depth manner so that we will get the accurates of triple RV and RRV.
Okay.
So they used to compare a table. Yeah, this is a comparison for a
Yes.
line system and a cable system. So can you
Yes.
see, like this is for line system? You can get a this is in
Higher.
time.
Yeah.
This is an RRV. So lesser the time, like you can feel the peak. But
Yes.
if you go to cable, like it takes some time because of the capacitance present in that.
Yes.
So this is how IEC IEEE have given some basic things like how to interpret or how to have the basic knowledge on TRV.
Okay.
So here also they will give some calculations. Like I'll let you know that how to do the calculations and everything.
Yes.
I'll just show you. Okay. Yes. There will be some calculations. Yeah. So this is some calculations they are trying to explain. But
Yes.
I have did the same calculations using IEC, not using
Okay.
IEEE.
Okay.
So I
Okay.
don't know the basic difference, but both are at the same. Like both the
Yeah.
formulas and everything are same. I have an Excel sheet for it. Like I'll have calculated it. I'll let you know that how to
No
calculate
problem.
based on IEC.
I will go through the IEEE as
Yeah,
well. It's good to understand when I get time.
there's a basic formula also it seems. So you can just
Okay.
use it.
Okay.
Fine. Now I'm going to explain with the thing which PSCAD have given, like the PPT.
Yes.
So we know that what is basic the TRV, which is system 1 and system 2, and the voltage difference is the TRV.
Yes.
So this is how a TRV waveform will look like.
Okay.
So we have to just zoom this portion and you can see the voltage difference. So something like this, yeah, something like this. It will be something like this. Here,
Okay.
if you like look at this time, it
Yes.
is smaller. They have just zoomed it,
Zoomed in.
and
Yes.
they are just trying to show it.
Yes.
So I'll just show you how they have modeled it.
Yes.
How they have modeled it. I'll just show you that. So pushing capacitance. Yeah. So there's a key parameter they're trying to show, which is the first one is the rate of rise of recovery voltage because that's an peak,
Yes.
and the remaining is the TRV
TRB.
wave.
Yes.
Mm. Yeah. So this is the envelope. This is the envelope I just want to show.
Okay.
Like technically or in IEC they have classified some types. Like I'll just show you the table for it.
Okay.
I'll show you for 400 kV, which is we are going to discuss. Yeah. So this is 420 kV. This is
Yes.
420 kV. Like our CB is 420 kV, rated for 420 kV. So
Yeah.
here, if you check the test duty, they have given
Duty.
for T100, T60, T30, and
That.
T10.
Yes.
So the meaning of this is 10% of fault current, which is again I'll show you the rated fault current for this. Uh, this circuit breaker's fault current I'll try to show.
Rated
So here, rated short time withstand current, which is 63 kiloamps.
ampere. Yes.
So this circuit breaker's rated short circuit withstand current is 63 kiloamps. So this is 10% of 63 kiloamps,
Yes.
and this is 30% of 63 kiloamps, and this
Okay.
is 60% of 63 kiloamps, and this is 100% of 63 kiloamps.
Okay.
So if my system has a 10% of 63 kiloamps, so
Yes.
I have a fault current, like from source a
Point.
fault will come,
Yes.
and based on the OHL or cable, like there will be some impedance and there will be some fault will just go down,
Yes.
and it reaches my circuit breaker. At,
Yes.
at, at the end of a circuit breaker, I have to check what is the fault current.
Okay.
And I have to check with the 63 kiloamps,
Yes.
and you'll get the percentage fault current.
Yes.
So using that, you have to compare with this test duty, like
Table.
T10,
Yes.
which is, yeah,
Yes.
this table. This is
Yes.
basically called the test duty. T10,
Yes.
T30, T60, and T100.
Okay.
So this is basically the test duty, which you are going to compare with the actual scenario where you will get a fault current. So you have to compare. You have to take this value and you have to convert the fault current to percentage, and you have to check with this value.
Yes. Yes.
So
Yes.
this T10 have a voltage 787. This is the kV voltage. This is the peak. This is UC, right? UC.
Yes.
So for T30 it has 687. Like if you just closely check, for T100 it will be 624. For
24.
T10 it is 787. For
Yes.
lesser the percentage, the higher the voltage it can.
Okay.
You'll have higher the voltage.
Yes.
So here they are trying to show the same thing.
In the form of curve.
Yeah, in the form of curve. This is the envelope. Like
Okay.
this is we used to call envelope. TRV envelope.
So how do we get this envelope? Like
Uh,
when we
we
run the simulation?
Yeah, we have a separate module for TRV.
Okay.
So in that, if you choose what kind of breaker you're going to use and what kind of strength,
Okay.
I'll
Okay.
I'll just show you. I'll just show you that as well.
No problem.
So projects. Put on link.
There's a lot of time I need to, read these things.
Yes. Yeah. Like
Lot of
basically,
time.
yeah, the theory is somewhat tricky. Like
See,
you
now
can.
see if I do this full time, like, and the way like you guys are teaching me, I think I will be like quite good in like another 6 months. But the the sad part is like I am sandwiched between little bit politics.
Ah,
Yeah.
okay.
But okay, we will see. But it's really great like to know like these key things, that again comes from like a lot of experience, and I am knowing them in like first time, so it's really great.
Yes. So when like if you have a like if you have done any one or two projects in TRV, then that's easy for you.
Well,
Like that's a,
the reason behind asking these files from you is that I am going to sit in my own time and I will do this like I am doing a project.
fine. Yeah,
Yes,
that will
because
help you.
I
That
will
will help.
yeah, because I will not leave like someone else to decide for me. I will decide for my own, and I will try to do this all information in my personal time, and I will create some sort of like notes and using screenshots and stuff like that for me, and then I can delete all this data. you know.
That's good. Like that would be helpful for you once if you have any project, and like if you have project, then you can easily take it up and you can easily do it.
Project will come, but then end of the day, what will happen is like the full time I will be told to do the earthing as I am expected, because that's why I was hired. So unless until I leave the job, I am not going to get the chance to do this on full time basis. Here is I am the main earthing guy, like that. Yeah. So that's why I am asking like these files from you guys, so I can set in my personal time like I am doing just now, and I can learn on my own pace, like for example today source modeling, and I again go through the video and create my notes, and then once I get some level of again further confidence, then I can build these model on my own using again your instructions. Yeah.
Fine. Like, okay, so this is a 220 kV cases. Like there are different cases that we will discuss that as well. This is one of the 220 kV side. Like so you have seen the SLE, right?
Yes.
So like I have not modeled anything 400 kV, only 220 kV I modeled in depth, in detail.
Yes.
So this is the circuit breaker I'm going to study. Like, can you see the circuit breaker?
Yes.
If I just double click it, this is the like modeling.
Yes.
So and this is the TRV block. If you go into TRV block, you can give some values. So
Okay.
since 220 kV, I have calculated it. So it is user defined. You can just change it as IEC or IEEE. That depends on you how you're going to do it. And
Okay.
if you just go into user defined TRV plots, then there will be
That's
some
how you can
values
plot.
over here. So it will create an envelope, something like what PS had shown.
Yes. Okay.
And you can so this is the actual waveform, and this is the envelope for the circuit breaker.
Okay.
So when you
And as
close,
long as that comes in that, then it's okay.
yeah, exactly. So when you closely look at the TRV, which is the first curve, right?
Yes.
This is
In,
T100 curve.
yeah.
T100 for the test duty
Inside.
T100,
Yes.
because it has a
Magnitude.
lesser
Yes.
magnitude, like which is around 61 or 62
Yes.
kV. But if you just consider T10, then that is 80, like nearly 80, which is T10.
Yes.
So I just ask you a question for like just a normal question.
Yes.
So this is the envelope I'm just going to get.
Yes.
So this is T10.
Yeah.
So I'm going to simulate a system. I'm going to simulate a case, and I'm having 9% fault, 9.5%,
Yes.
and that curve is something like this. So
Okay.
this is T10 curve. So like, what will be your inference from this? This is the like TRV curve.
Yes.
So this is the envelope.
So that magnitude is basically higher than the
Mhm.
T10.
Yeah. So then we can conclude that this circuit breaker will not
Go
work
the
or will not
fault. Yes.
open.
Yes.
Yeah. Under if you have a 9.5% or lesser the percentage.
Yes.
Okay. Let us have another system. So this is T50. Let us
Yes.
assume this is T50.
Yeah.
Right. And the same thing, it has T90.
90. Yeah.
So sorry, T10.
10. Yeah. Outsider will be less. Yeah.
Yes. So I have a system which is around 45,
Okay.
and this is something like this.
Yes.
So what will be your inference from this?
So there will be a problem because it's crossing that.
Yes,
So
you can't.
51.
Yeah, exactly correct. Like it's 45% of fault current. You have to compare with T50 test duty.
51. Yes.
You should not compare with T10 test duty.
Yes. That is far from it.
Yeah.
I
So
can compare only whatever is less than T10.
yeah.
I can compare that with T10.
Yes, exactly. So there are different types of test duties: T10,
Yes.
330,
Yes.
and T50.
6. Yes.
If a fault current is 11%, what value you should take?
I should take T30.
Yes, you can take T30,
Okay.
or you can calculate for T11 also.
Oh, there is a
This is
method to calculate. Okay.
yeah, there is a method. There is a calculation IEC where
Okay.
Even for IEEE, there is a calculation. Like there, you can calculate for T11. You can
Right,
calculate
right.
for T12.
So these standard bracket you are showing like 30, 60, 50,
Yeah.
they are only just on a like some interval. And then if there is a some interval between these, we can calculate.
Yes, you can calculate.
Can you just
Okay.
to go back to this standard, Gokul?
Yes, sir. IEC, sir.
Yes.
Yes, sir.
Yeah, here you can see also like T10, T30, T60, T100. So
Yes.
the standard specifies or insists the manufacturer to test and prove the values at all these values like 10, 30,
For
60 and 100.
yes. Yes,
Okay,
yes, yes.
so means what say when he's doing a type test, he will prove with all these values. But in
Okay.
between, if any other, means what say our fault current divided by the short circuit rating of the breaker, not always like 10 or 30 or 60 or 100, correct? No.
Yes.
So that you can use a formula and you can probably means what say find out the value for corresponding to your fault current.
Okay. Then one thing on this, like as you explained in the beginning, like most of the time we do these studies at the last, you know. So if my study proves after a substation like in process or substation being installed that it is not okay, so do you think like they will replace the circuit breaker?
That's really a tough call to take it actually. That's where the problem is also. So
Yeah,
90
yeah, you
percentage of
explained that in the beginning. Yes, I remember. So
yeah.
that's why I'm asking, like, if my study says, or let's say substation is not built right, so how seriously someone is going to take this report if I do a TRV and there is some substation is like in inception phase or in like a construction phase, and I say like, okay, this is how it should be. So will
Yeah.
they like take it seriously and go and give it to
Yes.
manufacturer and get a new circuit breaker,
No,
or they come
that's
back
not
to
even
you?
possible, no, because the same dimension of the means the circuit breaker will be different. Your foundation might have already done,
Yes,
so
yes,
that
yes.
there could be
That's what
quite
I'm.
a lot of challenges. So
Yes.
answer like means what say it's all about a probability, correct? No,
Yeah. So we
so
are only just thinking about what would be the acceptable failures.
correct. And reality is like means what say it's all a question of like means what to say not a science. It's a question of like what's the decision which we are making. So
Yes.
from there like what we can understand is there any probability of failure? It doesn't mean that the breaker will fail, or is it mean like the
Yes. Yes.
equipment will fail?
Chance.
So there is
Yes.
a
Yes.
probability that this equipment can fail, and
Yes.
probably means what to say means but the scenarios are both the sides like there are some systems where the result shows that probably means for say there will be a problem, so there is a probability, but despite of that means for say the customer accepts that yes there is a risk and he go ahead, and probably
Okay.
such a power substations are operating for 25-30 years without a problem.
Yes. Yes. Yes.
But that means like that scenario, worst case scenario which is expected has not arrived in the real time. But
Yes.
on the other side, I have seen quite a lot of substations where everything is proven. Like means what say TRV is within the limit, triple RV is within the limit, like VFFO is perfectly done, this one is done, etc., etc. But still,
Then there
I
is
mean
a
what
fault.
say there are means what say equipment failures, especially the reactors at 400 kV level. That faults are like that problems are really I mean what say severe. Despite of you have point and wave switching, despite of you have sophisticated mechanisms, etc., etc. So probably means what say then it will result as like a root cause analysis, but even root
Yes.
cause analysis will not be able to find out the real root cause, because like each and every manufacturer, consultant, contractor, everybody will try to safeguard them during the root cause analysis, correct? No, they will not say that that
Yes.
my product is a mistake. So root
Yes.
cause
Yes.
analysis without the real this one goes waste, like so we have also done quite a lot of such things, but means was say it's all probably as a more or less like a documentation sake rather than like a real application or a real impact sake.
Yes, yes. I was just trying to correlate between like what I do. Sometime like if there is a problem in the system and it doesn't comply with like in terms of earthing, and I say someone to like do this, so they are legally bound to do that because it's their job to protect people, from the dangerous voltages, whether inside sub or outside subs, you know. So if I say something, you need to do it. So they got a liability to do it because if some health and safety hazard happens, so they go
Correct,
behind the bar.
correct.
Yes. I seen this all switching and all this creating some problem in earthing as well. Uh, Like I don't know about the TRV because this is only I heard last year. Before that, I didn't even know. But this switching, lightning, and stuff, there is a working group where I am in. To be honest, I didn't do much on that. But what it does is it discuss the impact of lightning switching phenomena on the earthing system, and then that impact on the secondary system. Once we finish this, or I will show you the some PowerPoint that we discussed. So it shows some accidents that happen in China, especially, and it tells that if there is a switching phenomena or there is a lightning phenomena, and how it can damage something because of improper earthings and grounding, and it does show for some of the GIS and some of the HVDC converters, something like that. But this TRV, I am not sure. This is not what I discussed. Like, so this is only I saw last year from a PSCAT webinar when I was thinking to do this. So I was just trying to correlate here. Like, if I say someone like this is a problem, will he do something for it, or just basically say, okay, this is failure, and he will take his chances and don't do anything? Okay, Gokul, please go ahead.
Yes. And Himanshu, like to your personal chat window, I have shared some type test reports also of circuit breakers. Like this T10, T30, T60, T100, they have tested, and they have that's a type test report from the manufacturer. I have sent it in your personal WhatsApp. Okay, so probably means when you're going through, like you can easily relate this with that.
Yes.
Right.
So you do you have any doubts on this envelope, how that is created in PS4?
Now I understand. Yes.
I can explain how that was created in PSCAT, but this is the basic. Like
Yeah. When I saw it, I was just saying like, how do you get like this curve? So.
Okay, fine. Okay, that. Yeah. So I'll just show you how they are modeled here and how we are modeled.
Yes.
So this is the basic circuit. Like this is the SLD.
Yes.
And they are modeled with the capacitance. So can you see the transformer? They are modeled with the straight capacitance, which LV to ground, sorry, HV to ground, LV to ground, and HV to LV.
Yes.
I'll just zoom it a little bit, like 3000 picofarad. These are straight capacitance, and they are modeled the surge resistor with capacitance. So this disconnector with a capacitance, so CT, and everything they are modeled with capacitance. So the modeling for the TRV will, like, you have to only concentrate on the capacitance, and you have to get it from the client. So from the client. So I hope you have this data with you.
Yes. The one you showed yesterday.
Yeah. So you can this. Yeah. You can get the capacitor to ground. Like if the circuit breaker, then you can take this is an grading capacitance between the contacts.
Yes.
And this is capacitance earth, which is a bushing capacitance, 225 picofarad. This is between the contacts, 7 picofarad, the grading capacitance.
Yeah.
So for each and every like equipment in the PSK, you have to model with the capacitance.
Yes.
So since TRV and RRV like are depends on the capacitance, so which you have seen
very accurate.
So it's a basic thing, like we have to model with the capacitance. So that's the same thing they have also explained here, and they are trying to give some fault, and we can see it how to give the fault and everything.
Okay.
So
if we don't get these capacitance, then this was I was asking. I remember that they were saying you can assume it.
Yeah. So you can take it from the IEEE C37. That is the standard which I have shown you. So
And does IEC tell you anything, something similar or not?
IEC they used to in IEC 60071 they have given capacitance value. Fine.
Okay.
Fine. Just give me a minute. I'll just open and I'll show it to you.
I seen the document, but I don't remember.
I'll just open it. Just give me a minute.
Because this is very important question. You know, as a consultant, if you ask data and it never comes.
Yes. So.
I am just.
For damn sure, you have to get it from the client. If
that I understood. But sometimes, the client is like, They are, I don't know what's the right word, but it's called in British language, prick. The guy who is fixed, is behaving bad, not trying to move. So some client are like that. They will just say like, oh, assume some of the standard and take some
So
standard
when
value.
you
So I need to know what it is.
yes, when you're trying to get some assumptions, like you have to get it from the standards or from secret paper or anything like that should be a standard value.
Okay.
Yeah.
For what equipment, Himanshu, you're asking?
No, this capacitance value, like this
The
bushing
capacitance for breaker or surge arrestor or breaker. Okay. So that's what like means what say. Can you just go back to this means ABB document, Gokul?
Yes, sir.
Can you just...
I have it. This one.
Yeah, this is fine. Like, can you just show the previous one which you have shown, no, from ABB document, like SP31 model?
Yes, sir. Yeah.
That one we were
So
discussing
this
before.
one.
Yes. Go to the first page. Yeah. So means what say means I'm just trying to project or trying to answer your question in a different way, Himanshu. Like means what say the same manufacturer. This is from ABB.
Yes.
SP3-1 is a one model. SP3 is a different model.
Second model.
Okay. And circuit breaker with the closing resistor SP3 is another model. Okay.
Model.
And SP31 and SP3, you look at the capacitance difference.
Yes.
Like capacitance to earth is 225, whereas here it is 295.
Yes.
At least okay, about means what's it 30-40% mismatch. But if you look at the circuit breaker in open position, the capacitance between the contacts, like means there it is a 7 picofarad, here it is 350 picofarad.
350 picofarad. Yes,
so
of course.
You got the point, no? Like means what's it? There is a huge change from the same manufacturer, almost from the same family of the breaker. Correct, no?
Yes.
So I mean, so what's the answer? Like means what's it? Though the standard like means what is it now? Gokul has shown, no? Like you can take some parameters. Can you just go to the Gokul, that one? Yeah. So you can refer something like this. You got it, no? They are selling like means voltage transformer, SF6 to air boosting, surge arrestor, CVTs, current transformers, everything. So these are all typical values. Okay. But in a reality,
yes.
But in the reality, means what's it? This numbers greatly depends upon the manufacturer. Okay. Yes. So means what to say? Once we have asked like means what to say the capacitance value on the HV side of the auto transformer. I mean, so to say that value is probably means what to say the manufacturer himself given 1400 at the beginning. Then we have run a simulation for 2 months. Means what to say everything is exceeding. Okay. Then we have gone back to them and now they have given 1000 picofarad.
Okay.
Sorry, 10,000 picofarad.
Okay.
You got the point, no? Like originally he has given 1400.
Yes.
Because means what say means we have run all the studies with 1400 and probably means what say everywhere the problem is existing. So now we have gone back to them like means what say this is a problem like that. Then he's giving okay, you take this value, it is 10,000 now. So probably means what say they are also not really clear unless otherwise this equipment is manufactured and tested. But as you rightly told, like means when the equipments are manufactured and tested, by the time breaker might be inside already. So probably then changing the breakers and all probably extremely difficult. And probably means by means of looking at this SP31 and SP3, you can also understand. SP31 is a single interrupter, whereas SP3 is a double interrupter. Correct, no?
Yes.
So yeah, means Gokul, if you can share, like, can you just Google and probably means was a double interrupter breaker model, something like that, capacitance model. Double interrupter GA's breaker capacitor model. Yeah. So, yep. Go to the image. Search with an image.
I think it does show the first one.
Right, but probably means also they have not really given like how it's to be. I'll try to find something and I will just try to share. Yeah, I will try to share some image like how it is modeled. That like a double interrupter and double capacitance will come in parallel. So I guess
No
like
worries. No worries.
okay.
No, the reason I was asking this question is like I just want to understand like every aspect. Sometimes you end up without information and you are asking, and then someone is saying like no,
Yeah,
you
yeah.
assume. So you need to know like what is the impact of this and what are the possible
Correct.
cases.
So IEC
Yes,
have given
I can
some
see that.
standard
Yes,
value.
yes,
Like
I can
you
see
can
that.
take it 100 and 150, but this
Yes,
is capacitance to earth, not the
yes.
great
Take,
capacitance.
yeah, just taken from again some reference. Yes.
Yes.
Okay, I understood it. Go.
Yeah. So the thing which is important here is you have to model with a capacitance.
Yes,
So the modeling for each study may be different. Like if
I
FFO,
can
the
see that
modeling may
now.
be different. For the
Yes,
TRV, the modeling is totally different. So on modeling, you have to be caution. Like you have to use in capacitance value. So since
yes,
the RRR and TRV or dictate or like it depends on the
by
capacitance value. Right?
capacitance. Yes.
So yeah. Yes. So okay. Let me go to a calculation which I have.
Yes,
Yeah. So can you see my screen? Like
yes,
my Excel sheet?
yes. I can see it.
Yeah.
Go.
So this is the same IEEE standard 62271 part 100, which is if you go to 144, like you can see this snapshot. I've
Okay.
taken that to show that.
Oh, I trust you, brother. I will see later on. It's okay.
Fine. Okay, like so there they have given some from a formula. Like
Yes.
the issue what we have faced is in IEC they have not given for 1.5, which is I'll just show you that as well. Like why we have went for
IEEE.
the calculation. Like yeah, I'll just show you that. Uh,
But before that, this FPC 1.3, 1.5, you are clear, right, Himanshu? What is
Yes, yes,
FPC
yes,
1.3 and
yes.
1.5? Yeah.
It is called
So,
your earth fault factor.
yes, exactly. Right.
Yes.
So,
This.
for a solidly earthed system, we go with 1.3, and I mean, let's say non-effectively grounded systems, we go by 1.5. Like you might be using this quite frequently in your earthing and other stuffs, correct? No?
Yes, I didn't see in the earthing as, and I mean I don't use that as such a lot, but I have seen in some protection studies report done by
Ah,
some other guy for us. Yes,
okay.
yes. It is called earth fault factor. I think it's because of I don't know, maybe British standard or
Correct.
because of IEC.
It's the same thing. Like IEEE calls this as earth factor. So here, like means we call it IEC 62271. We call it as like first pole place factor.
Yes.
okay, so this is a 220 kV data sheet, like the switch key data
Yes.
sheet. Here we have a circuit breaker which I have shown like recently, right? The rated voltage is 300 kV. So
Yes.
similarly, the first pole to clear factor they are given as 1.5.
0.5. Yes.
So you have to take these. You have to just search for a 1.5 earth factor. Like I'll just show you that.
Yes.
So this is yeah, I'll show you that. Yeah. So this is an S1 which is in IEEE we have talked like below 100 kV, that is 2 parameter, right?
Two parameter.
In
Yes.
IEC they used to call it S1, class
Okay.
S1. Like
Yes.
S1, which is they are given for KPP 1.5. Since our KV is 200 kV, right?
200.
300 kV.
300. Yes. It
So
will be
we have to
above
go for
100.
yeah
S2.
S2,
Yes.
S1 circuit breaker for 1.3.
3.
So we don't
Yes.
want that. Yeah. So this is S2, which is
S2.
for
Yes.
1.5.
1.5. Yes. And then we
So
need to see 300.
here also they have given up to 72.5. Like I'll just show you the thing. Yeah. Fine. Here they are given rated voltage of 100 kV to 800 kV, 1.2
Yes.
to 1.3. Says
Yes.
1.2, but we need 1.5, right?
0.155. Yes.
So 300 we have only 1.3.
Yes.
we don't have table for these values for 1.5.
0.5
So that's why we went for a calculation. So
calculation.
if for example, if you're using 1.3, then straight away we can take these values.
Exactly. Yes.
These TRV peak value and this time value. But since for 1.5 there is no table in IEC, like we have went for a calculation. They have given a separate or a formula for that also.
Yes.
So that's what we are going to see.
Yes.
So the formula is 0.75 into KPP into UR, which is rated voltage, and
Yes.
KPP is 1.5. We know that we took from the data sheet. And
sheet.
UR is the rated voltage, which is
Rated
300
voltage of
kV.
circuit breaker. Yes.
And square root 2 by 3. Like that's the same thing. 0.75 into 1.5 into
Yes.
300 into square root 2 by 3.
Yes.
So, which is reference voltage, we got 275.568.
Yes.
Which is U1.
Yes.
Is U1. Then so the same thing you can take for the T100 peak value. The same thing you can take, like 100 into 300 into 1.4. The same thing, like you can take it from here, like the TRV peak value, right? You
How
see
that 1.4 came again? Because we were using 1.5. I may be confused here.
Yeah, KAF.
Oh, KF, right? Okay.
Yeah, so
Yes.
I took it from here. Like this is the value I'm going to, like this for T. So
Yes. Yes.
I'll just show you the
That
TRV
column
peak
you want.
value. Like
Yes.
I'm taking with T1.4. The 300 peak value I'm going to take.
Yes.
I took
1.
T1.4 and I just
Yeah.
like calculated it.
Yes, I get it now. Yeah. 1.5
Instead of,
multiplied by 1.4 multiplied by that value. Yes.
instead of 1.3, I'm just replacing it as 1.5. That's it.
1.5. Yes.
That's the difference. That's the only difference I'm having it.
Yes.
So the same thing. 1.5 into 300, which is the rated voltage UR,
Yes.
and
Yes.
1.4 into square root 2 by 3.
2 by 3. Yes.
So you'll get 1514.393. So similarly for T60, you have to
Yes.
take the value. You have to go to this table. You have to take this 1.5 as KAF,
Yes.
the amplitude
Yes.
factor,
Yes.
and then you have to calculate.
Then 1.54 and then 1.76. Yes,
Yeah,
I get it now.
and
Okay.
1.76. So this first step you have to calculate this with this KP and with this KAF and this
Rated
this
voltage of
rated
circuit
voltage.
breaker.
You can calculate this. Next thing is the first time, like T1.
Yes.
So you have to get it from the RRV, like triple RV. I'm sorry, triple RV. So this triple RV is kind of constant. You can just check it, like 2, 3, 5, 7, and 1.4. Even for 245 kV, which is 2, 3, 5, 7, and 1.54.
Yes.
But the only thing changes is the U1 and T1.
Yes.
So the triple RV rise formula is U1 by T1, which is U1 is the first reference voltage which I have shown you, and T1 is the time taken for it.
Okay.
So the time, the voltage divided by the time is the peak, right? Like
Right.
at the minimum time, you
Rate of
can
change.
get the peak. So I have like took this value as a constant value 2, 3, and 5 and 7.
Yes.
So I'll just show you that. So we know T1 is equal to which is RRV is equal to U1 by T1, right?
Yes.
So you know RRV.
Yes. I can get
And you
T1.
know
Yes.
U1. You can
Yes.
easily get the T1, like which is
T1. Yes.
U1 divided by RRV.
Yes.
So similarly for the T1, first time T1, I have done the same thing. I have took the RRV for T60, T30, and T10,
Yes. And
and I
divided
have
by that.
used this as constant and like just like divided by the reference voltage U1.
Yes.
U. So this is again a peak time, and this is again a peak time. Next, the T2. So the same thing, they have given a formula for that as well. 144, I think so. Yes. Yeah. So the time T2. So this is rated voltage from 100 kV to 800 kV, which is our voltage is 300 kV, right? So
Yes.
this is the column you have to look, and this is the voltage I have like snapshot, and I've shown there in our PS like on our Excel sheet. So
Yes.
the time T2 is equal to 4T1.
41.
The test duty T100.
Right.
And T and time T2 is equal to 6T1 for the T60.
T60.
This T2 will be only available in T60 and T100. I'll just show you that. Yeah. So this is T2, right? Like T2
Yes.
or T3. See
Yes.
the time available. Like the remaining time, which is T1, is not available for T30 and T10. Only it's
Yes.
available for T100. That's why I have calculated this T1 only for the T100 and T60.
Yes.
So now you have the formula, which is like the T2, which is 4 into T1,
Yeah.
and
And
for
then
the
6
T2
into
is 6 into T1.
6 into. Yes.
So now you have all the values.
Yes.
So now you have the all values. Like you have to put it or insert in the PSCAD model.
Yes. Model. Yes.
I'll just show you that. So this is 220 kV.
Yes.
The first thing what I have to do is I have to give user defined. I should not go to IEC or IEEE, because since both the like IEC I don't have the 1.5
Yes.
K, so I have given user defined, and remaining
Yes.
thing you can just leave it as it is. Next
Yes.
you have to go for user defined TRV plots.
Yeah, fine.
And here you have to get some value. I'll just say that. So same thing, the reference voltage for T100
Yes.
275.5. I have just rounded it
Yes.
up and 276.
Yes.
T100 first time 137.7, 138.
Yes. Okay.
So
I get it
similarly
now.
you can
Yes.
give
Till all the time. Yes. And see if you go to the IEC options, right? So is that list like all of the options, like whatever you want to choose?
IEC they will give S1 and
TRV
S2.
class.
Like if
S1
I
and
go to
S2.
S2,
Yes.
like there will be some addition duties they will give. Like I'll just show you that as well. Like this is the rated voltage you have to give.
Okay.
So let me give 300 kV, which is our kV, right?
Yes. Yes. That's what I want to understand. Yeah.
This like 100 to 180 kV.
Yes.
Then
And
I have
then
300.
300. Yes.
Yeah. Then if you check this, like this, then it will take the standard value of 300 kV, and while
Automatically.
yeah, automatically it will take it.
Okay. Okay. I
I'll
get
just
it.
show you. I'll just show you one of the 400 kV side also.
Okay.
I have to check it.
I was thinking it will populate those values there, but it will take them automatically from somewhere in the reference. Yes.
Yes, so I'll just show you that. So this is again a 400 kV TRV.
Yes.
So I'll show you the overall system. So only sorry, yeah. So this is the 400 kV system, right?
Yes.
Like 220 kV I have not modeled it. So only 400 kV is my scope. So I'm just modeling it. So you
Yes.
go to this data, not this one. Yeah. Here I have given, because
Based on the IEC.
420 kV based on IEC I have given 420 kV.
Okay.
So what will happen is if you go,
It will
this is
come.
equal.
Yes.
If you just show this, it will like it will just show you, like while after simulating it, it will show you different types of plot. Like
Okay.
you can take the plot.
Yes.
Here you are going to measure the fault current.
Yes.
Like you are going to measure the fault current, and it will show what is the fault current while opening a breaker. Like this is the old circuit, hold HOLD. So
Okay.
using this, we can try to know the fault current while the breaker is opening.
Opening.
So
Okay.
basically what this will do is it will just capture the value if there isn't any change in the breaker. Like if
Breaker.
if it is opening or closing, at that instant it will take the value and it will show it.
Okay.
So by that, like you can get the value, right? Like the fault current. and and with that fault current, you can easily choose the envelope, like it's T10 or T30 or
Yes.
T100 or something like that, based on the fault current.
Okay.
So up to this, do you have any doubt, like on the
No,
calculation part and
no doubt.
yeah? Okay, okay. Fine. Okay, just give me 5 minutes. I'll just drink some water and come. Just 5 minutes.
No problem. No problem. No problem. Take your time. I will come back as.
So, Himanshu, yeah, Himanshu, like in your case, like how this like requirements, I mean, all these projects, like they will ask TOV, SFO, FFO, BFFO, TRB, and
It
ferroresonance, or how it is?
it depends. I will show you one specification.
Yeah.
It depends. It totally depends on the client. We never done this. This inquiry came in, and we keep saying no, 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 no. But last year only, in the lockdown, like there was some like knowledge share or some email like what you want to learn and how you want to be and stuff like that from a sector leader. And I said yes, I can do something for you. If you want, I am interested to learn, and I will also show you how I moved towards this transient and all. I done some in CDAX related to earthing, but so the first thing is if you want to see that. So this is one specification. It will be done by now, maybe someone, but it shows what is required to be done. So it tells you the project classification. And it asks for a switching study, a reactor switching study. So here in this one, they are saying they are replacing basically a reactor. So they are saying we need to do like all the surge arrestor placement on the GIS. Apologies. Yes, the GIS, and then this separate part is this TRV. So this is only the one spec I have, and this is a further specification for TRV. What circuit they want to include and what they want to exclude. So it's not like a whole thing. So it was just they were converting this to I think they do mention here.
Is there any specific reason in this project they are replacing the breaker, or?
They will mention like it will be blah blah blah. The substation or the connection there.
Because like means what to say, I think like all other things are
they are
taken care
saying
already.
so it's saying based on the conditional assessment of existing asset carried out using this existing air blast circuit breaker has been identified for the replacement for REO-T2 period. So what here is there is a organization called OFGEM, Office of Gas and Electric or something. So it is a ministry like our power ministry. So same is a ministry. Then every utility here is basically private. Nothing is government. So these people change their tariff plan. The tariff plan, like before it was something else, now it is something else, and then based on that they basically create like a competitive environment for the people in UK, and then that's the way like the customer get like end customer get benefit. So for that purpose, they are keep coming with these new plans. So the recent one is called Rio T2. Revenue is equals to something, I don't know, it's something it has to do something with that, and then everyone is like upgrading their line. So this here is in like this all area, you can see it's called Scottish and Southern Energy Electricity Network. This all area, this is a Scottish Power, and this all together is a Scotland. This whole area, this even these island and everything. Now this here is Northern Power Grid. This here is Electricity Northwest. Then here is again Scottish Power South, some of it. Then this all black is Western Distribution Power, and then UK Power Network. And then National Grid does operate the long electrical line in all these areas, because here in Scotland, these two companies are transmission as well, distribution as well. Scottish Power and SPEN, right? This whole area, and here as well. But in down south, 132 kV is operated by all these companies: Electricity Northwest Power, UK Power, and Western Power. All these here, and then this transmission above 275 and 400 kV, including the substation owned by National Grid, which is not shown here, right? So these people are coming with a plan like I don't know what it's called, T2. It's called I was some written revenue is equals to something. So it's like a price control review of GM. So it is controlled by them. I forget the name, but I will ping you whatever it's called. Then for that purpose, they are keep renewing their system, like upgrading their lines in the north and south. So that's why they were replacing this. So they explain like it is connected to like so many substations, like this 400 kV, this all this, and then what substation is actually Windy Hill, right? And this is like a substation, how it's look like. And then the scope wise, they ask like they want to do an insulation coordinates study. All they want is basically list all scenario and everything, and basically do a surge arrestor placement. Basically, this is what they ask here. And then another one, they ask transient recovery voltage, and then further they specify the transient recovery voltage, what fault they want to do. And then I think there was a switching as well, reactor switching or something, and this one or and another one I forget. Yes. So this will be a copy paste spec. They just change the substation name and they send you everything same time. Like sometime I get other inquiries, for example, for earthing. So the specification are always the same, copy paste mostly.
Understood. Yeah. That is most of the time that happens. Yeah.
Yeah, so this is what
and they're specifically asking in the ATP EMT software, correct? No,
that's what I am saying. Like this is coming because somebody who have done this study would have wrote a specification for them. So for example, I get a earthing specification, right? I will show you that. So I am doing a earthing study. So it was a tender. So somebody wrote this specification, and then it is a normal earthing study. It's not like any like hi-fi requirement or something. So but it still mentions CDAC input and output should be CDAX version 13. Version 13 was before I joined SES in 2014 or something, right? And then CDAX high frec and FFT SES. This is only for the high frequency transient. Like you do earthing using that, but nobody does. It's very expensive. And this module is solely for reverse Fourier transform and forward Fourier transform. Like it has nothing to do with like normal earthing study. But it's just a copy paste. They don't understand. They just copy paste. Then you need to tell them like, no, this is wrong, or this is not what it. And AutoCAD 2007, like what you will do with that? I can't even open a file. So it is just copy and paste most of the time.
Right.
Yeah. So whatever software, like if I go in this company and I work them and I put a specification, and they will use that blindly for so many years. Yes. So this was the only one inquiry that I was involved in, and there was one related to the tower as well, I think. Just because that's why I was asking for this. No. Yeah. So basically, yeah. So that one, this one, this. But there was some query. I think it was in the email. So can you say it does mention like this year? Lightning performance study to be carried out in substation, or thing to ensure specified performance study to ensure the substation of my design is achieved. So I do again something normal study is called often frequented tower, which means those transmission line tower which are in certain area based on the standard, like in farm field and so many area, you can go there and you can touch them, and they are called often frequented tower. Might have here, but not at the moment. So this is, and that I was saying, like how I converted to this, because I joined this working group based on a suggestion from a client. So this working group deals with the it deals with some transient phenomena, right? So what it is basically evaluation of transient performance of grounding system in substation and its effect on primary and secondary system. So this transient phenomena, how it happens is because of this lightning switching and everything that I am learning from like you guys. But this is not what I care. I care is like when it is discharged to the earthing system, when it happened, what happened after that to the equipment, to earthing. And certain type of, not related to like really insulation coordination, but certain type of like electromagnetic compatibility type thing. So what they are saying is that they've done some study and measurement as well. So they are trying to match the CDEX value and other values on certain things. So that's just a generic CPT. So these are the incidents that I was saying, right? A converter station, the lightning caused something to fail, something to block, the transient short circuit failure. It's a vague term, transient, it means several things. Like you guys know this, do this study, so you know. So these are the things. So like this card punctured and relay and other stuff. And the target of this was to like define and classify like what are the transient characteristics for the earthing purpose, not for the insulation coordination or other purpose. And then review the simulation method, like what are these methods and impact, and what is the impact on the primary system, like in general, not like defining insulation coordination or something, but just to tell like what can happen because of these poor grounding.
Right.
And then review some documents, and I done like very little on this working group. I didn't do like much, but this is what they are doing. Then there was another document on this one somebody sent me. I didn't get a chance to attend any working group meeting. I just done everything remotely.
Okay.
Because company don't pay you to travel, as simple as that.
That's right. Okay.
Yes. So this was I think one of the so I think not this. They were doing some measurement. I might have forget, but yes. So this one. So what they have done is they done some measurement like on these stations. I am not aware of that. They are trying to record some measurement, like if we use the surge generator to generate a surge, and then how your system behaves, and they are trying to measure like different voltages on these equipment, like in the GPS termination and bushings and stuff like that, and then it will come up with like some conclusion, like what transient they injected from which point and up to what hertz it was injected, and how we can verify that our system is performing all right or not. So this is what I have done, and that's why I was highly interested to do this, to understand it like in a full way. This is about to end, and when I was in is 2018. So yeah, the brochure is due to publish soon, and then once it published, then I will share with you what it is.
Sure. Yeah. Thank you.
But it was all related to like earthing, in terms of earthing, like not related to other stuff. Yes.
Yeah,
So
yeah.
these how the specification comes in. So before everybody said like no they are not available. Last time a company tried to send someone to PSCAD
Mm.
course, but
Uh,
the fact here is like I'm not like disrespectful to someone, but the people just comes like, oh yes, I will do it in a big confidence, and
mm.
then they don't work hard, right? They
Oh,
think like if you go for something and then it will automatically happen kind of thing, and then they will do just anything with a
mm.
great confidence, just anything,
Mm,
and
mm.
then they will submit to the client, and when that comes back, then only you know the reality, like what they have done.
Right, right, right.
Yeah. So
Yeah.
one guy was like that last year, and then they changed plan or something. So there was some session from our leader, and I say yes, I am interested to learn this, and in fact I was trying to learn on my own using
Mm.
ATP, MTP, almost impossible software to use,
Correct.
and I went nowhere with that. Yes.
Mm, mm.
And that's the reason like I'm learning from you guys.
Okay, okay. Got it, got it. Yeah, Gokul.
Yes,
Yes,
sir.
Google, please.
Yeah, yeah, go
Yes.
ahead, go ahead. Yes.
Yes. So, can you see my screen, Himanshu?
Yes, I can.
Yeah. So now we are going to talk about the modeling part, how that is modeled.
Yes,
So this is an like the model of our substation. Like how our SLD is. Like are you
yes,
aware of
yes,
it, right? Yeah.
yes, yes,
So this is RAF and the same source and the cable I have modeled.
yes,
And then this is an Salaya Super, which is an OHL.
yes,
And the surges have to be modeled with
yes.
a capacitor to ground.
So in this one as well, we need to model the full system.
Yes, yes. Full system is a detailed model is required.
Yes. Okay.
So we are going to study this breaker.
Yes.
So I'll just give you the overview how to model this.
Okay.
So like I'll just show you the this VT starting from VT.
Yes.
Like this is model as a capacitor, which is 80 picofarad.
Yes.
So where I took this value, like the
Data
document,
sheet.
which
Yes.
yeah, same thing. So when you come like voltage transformer 80 picofarad, capacitance to ground.
Yes.
Then a CT, like this is CT.
Yes.
So again, this is modeled
Yes.
like 48.01 picofarad. I'll
Yes.
just show you that as well. CT, yeah, see bus duct below, like capacitance to work.
Yes.
Yeah, bus duct is over here,
Yes.
which is 55.7 into like we have to divide by like we have to take the meter, like you have to consider the length of it and you have to give.
Yes.
So because since it is in PF picofarad per
Per
meter,
meter. Yes.
so you have to take the length of it. You have to get it from the AutoCAD file. You have
Yes.
to measure the length and you have to give the inputs to it. So
Yes.
similarly, so this is an disconnector, like disconnector switch. So this
Yes.
is sorry. So this is grading capacitance, right? Like this 4.2 picofarad is the grading capacitance,
Yes.
and this is the capacitance to it for the disconnector.
Yes.
So you have to model all the equipments with respect, like all the equipments with capacitance, and the values you have to take it from here, like in this document.
Yes.
So similarly, I'll just go to the capacitor, like the circuit breaker, which is going to get modeled, like which is we are going to talk about this capacitor.
Yes.
So sorry, this is circuit breaker. So before that, we are going to introduce a fault, right?
Yes.
So we have to introduce a fault, and we have to check what kind of fault we have to check, and we have to check what is the percentage of fault, and with that percentage fault, we have to check the envelope.
Yes.
So we have to give some fault. Like here, I'll just show you where I've given the fault. Uh, so cable. Just a minute.
No problem.
Hold. So this is the fault, like this is the fault block, like which the module which you have created. So you can insert where you want. Like if for example I'm going to insert the fault near the capacitor, near the circuit breaker, I can take it and I can just insert here.
Okay.
So this is
And
the
what is
fault.
inside that block?
Like
Just the
inside this
normal.
fault, so we have created a logic, something like that. We need a multi-run, and
Okay.
there is a logic.
Yes.
So generally I'll just take a fault and I'll show you that. So this fault you can manually give, or you can
Yes.
externally give the what kind of fault you are going to give.
Yes.
Like fault type control, you can give internally or externally. Like if I'm going to give external, then there
Yes.
will be a separate node that will come out, and you have to give externally. Like
Oh
for
yeah.
the
So you. Yes, I get
yes,
that. So now you choose the fault class from code from them,
multi-run.
PSCAD, and
Yes,
that's how you are going to control them.
yes, exactly. Like if
But
you
in that,
just go,
yes.
yes, Himanshu, yes.
But in this button, this radio button, you got like one no fault, two AG fault, three,
Uh,
right? So how do you know when you press the three is going to get the code 7 ABC
mhm.
for?
Fine, I'll let you know that. Like first, if you go to L file, they will tell you like for 0 it is no fault. For
Yes,
the
I
number
remember
1
this.
it is phase A to ground, and
Yes, yes,
for number 11 it is 3-phase fault ungrounded. Like
yes,
what I have to do is I have to open this.
yes. Oh, so sorry. Yes, you gave the position number and then
Yes,
data inside that. Okay, I
for
get it.
the position 0 you can give
Yes,
0. For
yes,
the position 2 you can give 1. For the
yes.
position 3 you can give 7.
7.
For the
Yes,
position 4 you can give 11, because these four fault I'm going to simulate.
yes,
Like
yes.
it
I
is
get it now.
AG, ABC and ABC to ground fault.
Yes.
So this is one type, like this is one type. The other
Yes.
type is you can just go
Multiple.
into this.
Yes.
You can create a second variable, and the
Yes.
second variable is enabled. You can just give list,
Yes.
and
And
then
then
you can go to the second variable and you can give the same value, like
class. Yes. Yes.
the same value. Like you can
I
give
get.
5
Yeah.
and you can give the same value, which is what fault you want to give, like 2 or 1, 7 and 11. You have to give something like this: 1,
Okay.
7 and 11.
Yes.
So, so if I give something like that, it will directly take it. If I give okay, then there will be some data label. I have to take the data label. I have to connect with the wire,
Yes.
and then I just double click FAULT fault. Then I don't want this. I can just
Yes.
connect a data signal.
Yes. And then you can give a fault to that.
Both are one of the same. Like
Yes.
this two is a one component, and if you just keep if you use the multi-run, then that's simple. Like always try to use the multi-run. Like
Yes.
this is the recommended modeling. Use the multi-run. Don't try to use this modeling. Like you can use this modeling, but every time you have to come and you have to like you have to
Click the
change
button.
this value.
Yes. Yes.
But if this multi-run, like just one run, it will just it takes some time to run. It will take
Yes.
around 6 to 7 hours, but you'll get the result with a neat manner.
6 to 7 hours
Yeah,
for
this
this one.
is
Like.
we have created 5 fault,
Okay.
and I just show you the basic thing.
Yeah, we need to look at the time step. No, Himanshu, like the time step is too low, and
Okay. So
probably
you are
means you have
implementing step.
multiple cases and you are putting it in multi-run. Yeah.
Yes. Yes. Yes.
So
Okay.
the
For the
time
time
step
on.
is 5 microseconds, and we are going to create a fault with different instance. Like here I have given two variables, like
Variable.
two things,
Yes.
right? One is sequential and list. You go to
Yes.
this real one calculation. Can you see at one at
All right.
like half cycle
Yes.
I have like the increment is 0.001.
Yeah. Yeah.
So
For each instance, it is going to simulate all those fault, and that's why it is going to take time. I get it now.
it will take around 6 hours.
6 hours is still okay. I am running a software for last 16 hours. Still half.
Yeah, that's right.
Yes, 6 hours is great. 6 hour. If somebody you say like someone CDEX user 6 hours, you're like, oh nice, fine.
Okay, then. So you have to do the all similar, like all possible fault cases. Like
Yes.
a single line to ground fault, double line to ground fault, double line fault, and three-phase fault and a three-phase to ground fault.
Yes. I can
This
choose I can only choose like 3 ground to fault and one 3-phase fault and one double line to ground fault, right?
either AB to G
Yes.
or AB to G and AB and three-phase to ground, which is 7, 11, 5 and 1, like single, like
Maybe a silly question, right? Is these fault happen in real world, like 2 line to ground fault or 3-phase fault? It happens ever. What is
three-phase
your
fault,
It's a
three-phase fault.
remote probability. So probability is much less, but
Okay.
still probably means consultants may ask, sometimes customers may ask. So, and the standard
No, I was just asking like your experience,
yeah,
like what
probability is very remote, like means less than a percentage.
Yes.
I can
Because
show you.
single line to ground fault can happen for so many reasons, but what about like these fault?
Okay, fine. Okay. Fine. Okay. I have read it in IEEE also, like what faults to be considered, like
Okay.
very basic. But I'll share you this. Like I'll take a snapshot of it and I'll share you it in the WhatsApp.
No problem.
So the possible like a possible fault combination you have to create and you have to simulate it.
Yes.
So do you have any doubt on this fault?
No, not
Model,
at all.
like,
Discuss this
so
lot
try
of
to
things.
do this model, which is important. Like this.
Oh yeah. I have done this before with the when we were discussing multi-run. So yeah, it's simple. I understand it.
Yeah, fine, that's good. Then the fault part is over. Then we can talk about like the circuit breaker.
But I will submit this multi-run for like these long instance so that I can see like how it run for 6 hours and what it does.
Fine. Okay. So this is the circuit breaker.
Yes.
So this is the capacitance that I'm going to model, like that's it. So this is the circuit breaker I'm going to study. So that's why I have measured the voltage on that, and this is the
Yes.
source side voltage and load side voltage, VL and VS.
Yes.
The VS is the source side voltage and VL is the load side voltage.
Right voltage. And that TRV is a voltage between those two poles.
Yeah,
Basically.
the between the two contacts.
Yes.
So this just an voltmeter. That's it. Like all
Yeah.
are voltmeter. So if you go to this circuit breaker, the same thing. Like here I'm then trying to give in the output from the multi-run.
Yes.
Which is like after fault 100 seconds, like if for example if it's the fault is happening at 0.3, I'm going to close like circuit breaker at 0.4.
Yes.
So I'm going to close at 0.4. So the output from the multi-run.
Yes.
So like I have taken from this. So the next is yeah, fine. So the next is this block. Like what you're going to do is we are going to measure the breaker status.
Yes.
I'll just show you that as well. If you go to breaker,
Close.
if you go to not this one, sorry. There will be some options called breaker status, like animation
Yes.
state, main data. This is breaker name, insertion data, internal output. Yeah. So the A phase or the A pole status, B pole status, and C pole status. Like status is an
Yes.
like normal post. So that is basically status. We have to take this. We have to take this status, and we have to give the input in the TRV block.
Okay.
And again, this is an TRV input, the over voltage that you are going to measure, that you have to give here.
Yes.
And this is the TRV output you are going to get. So
TRV.
each three phases I'm going to like I'm going to see all the three phases independently. Like for the A phase I have to check, for the B phase I have to check, for the C phase I have to check.
Yes.
So that's why I have used a data tab, and I have segregated all the three phases as 1, 2, and 3, and I have plotted it.
Yes.
So this is the envelope we are talking about. Like if you just connect with this, then you'll get the envelope. Envelope A, envelope B, and envelope C.
And what is exactly inside this full block?
This is the thing we are like whether this is user defined or the IEC.
Right. So this TRV block you get by default from the main library.
Yeah. Yes. So this is 4.5. So you don't have this in our library, but in 4.6 and 5 there is an like there is a separate block for this. I'll just show you that. There's a small difference on that. I don't know, like where is the block? They have shown that, yeah. So this is the block. So here also the same thing. Like you have to give the breaker status,
Yes.
the TRV output, and the envelope.
Okay.
Okay.
But I have now this module. Like separate.
Yeah, you can just check it. Like the same thing, but the module is different. That's it.
Okay.
So this is just created for 4.5. For 4.6 and 5, they have created the module, like the different module. That's it.
Okay.
So the breaker status I have given, the TRV, which is the breaker voltage I have given. This is the TRV output. The output I'm going to measure that I have taken, and this is the envelope. Like based on the KV and based on the IEC standard, like if you give these things, then you'll get an envelope.
Yes.
So then the next thing is then the next part is yeah. So if you go to breaker, I have measured the fault current or the current breaker current. Like I'll show you that. Yeah. So this is the breaker current, right? IA, IB, IC. I have measured this. I have measured. I have to know the breaker status also. I have took two values from here. So this IA, IB, IC.
Yes.
I have used this. This is a single phase, so I can just convert to RMS because this is in peak, right?
Yes.
I want an RMS, so I have just used a single phase RMS meter, and I have converted from the peak to RMS, and I have named it as IAA, which is the RMS voltage, RMS current.
So
And that also I'm just trying to plot it. That's it.
Okay.
And then this IAA I'm going to give here.
Yes.
This that is going to divide by 63, so you'll get the fault current, right? Like this is if you just this is where you're going to get the percentage or the percentage fault current.
So
Like
IA is coming
fault,
from breaker. Right?
yes, exactly.
And then 63 you are sending.
Yeah, this is the
Total
circuit
fault
breaker.
rated current.
Yeah,
Okay.
63 kiloamps.
Kiloamp. Yes. I get
So
that.
the basic for the normal current divided by
Divided
this is the fault current divided by the
rate.
breaking. It's a rated fault. It's a rated current fault current withstand current into 100. That gives you an fault current percentage.
Yes.
So this is the fault current percentage. I'm just going for this is for A phase.
Yes.
So I have measured it, and I'm just going to record this. That's it. And I just want to plot it. That's it.
Okay. And
So
what is
this
this
is
multi-run doing here? This one again?
it's just going to measure that. That's it.
Okay.
Number of channels to record one, recording unit one, like the output channel is per SC, and it's going to measure the maximum. That's it.
So it is called multi-run recording.
Yes, this is one type of multi-run which is used for recording.
This is exactly I was asking when we were running the lightning example. You know,
Uh-huh.
so I was saying like, can I increment this lightning current by say maybe another 10 kiloamp, 10 kiloamp, 10 kiloamps, and so on, and then I can record how many times there is a flashover occurs.
Okay. Yeah, even one of the PS card example also they did the same thing, right?
Yeah.
Yeah, look, yesterday we were discussing that. Like
Yes.
with
Yes.
this
Okay.
with this you can record it.
Oh, nice.
So
And that another plot where you are sending time in from this, so it is
so
part
this
of it.
This is just a range comparator. That's it. Like it's just going to measure with respect to time. That's it. Like this is in time, which if you try to change this value, if you change this value, it will change. Like so the time which will take like 5 microseconds, right? So the same time
Yes.
it will take. It's an you can get it from the component. No, you can get it from the master library. Just show you that.
Okay.
See here, like this.
Yes.
So yeah, so this is for A phase. Similarly, you have to create for B phase and C phase.
B phase, yes.
Yeah. So I'll just show you that. This is for C phase,
Yes.
and this is for yeah, stop. This is for B phase.
Yes.
So now I have the fault current for A phase, B phase, and C phase,
C phase.
and
Yes.
the percentage fault also I can get it.
Yes.
Now what I'm going to do is I'm going to get the at the instant of breaker closing or opening, like at the instant of breaker opening, I'm going to get the fault current. I have to know the fault current. Then only I can refer from the, or I can refer, or I can like see the plot, or I can whether say this is T10 or T30 or T50, right?
Yes.
So we should know the at the instance of
Instant.
breaker.
Yes.
So this breaker hold, right? Like this is hold circuit, HOLD, sample and hold. Like if you give the input as fault current, and
It is
if you
coming
give
from
the breaker, like
yes.
here you have to give the breaker. Like if the breaker is, or like for normally that would be just a minute.
It should
So
be
this is normally closed, right?
yes.
Yeah. Like once if the breaker opens,
Yes.
if once a change in the breaker, like if once the breaker opens, it will change, right? Then that will exactly take the fault current and it will just show it here.
Okay.
So
So that BRK is coming from the breaker on the top with what we have modeled, right?
yes. So this is the BRK.
Yes.
Like the breaker name.
Yes.
Like the breaker name.
Yes.
So for this, I'm going to measure for fault current A. So similarly for fault current C and fault current B, I have to measure.
Okay. So is that breaker is when you are like keeping them same BRK? So is how it is exactly reading them as three phase, not just as a one?
Okay. Fine. Okay. Actually, this is not an I'll just show you that. This is not a single pole operation, right?
Yes.
So all the three
Okay.
phases.
So yeah, it will be the same. Yes.
So
I get it.
if it's a single pole operation, then what you have to do is sorry.
Then identify three separately.
Yeah. Exactly. Like you have to give. Sorry. Yes. Then just go to this, and you have to give breaker A, breaker B, breaker C. Like
Yes.
for the B phase, you have to give breaker B.
Yes.
Similarly, for C phase, you have to give breaker C.
Yes. I get it now.
Something like that. So
But there's
here
no
you
point
have
of
to
doing
give,
that here, right?
yeah, now there is no point on doing that.
Yes.
So do you have any doubt on this whole circuit, or do you have any like
No,
how it
not at
like
all.
operates, or how it fine, like you okay with this whole circuit, right? Hold.
Yes. I just need to digest this logic, like from where it's coming and from how it's taking. I know what it's doing, but kind of memorize it. Yes. I get it. It's clear. Yes.
Okay. I'll try to do a test circuit with just an circuit breaker or source and connect this, and at 0.3 seconds try to like open or close the breaker, then at 0.3 you can get the fault current like here. So you can create a test circuit, something like that. If you
I
can't
will do.
understand this, only
Yeah.
take this and create a test circuit and try to simulate that.
I will do.
Yeah. So again, this is TRV. Like this is an like derivative. Like it's an just an like the TRV A phase is just derivative. Like which an like what to say TRV, or like the basic formula for TRV. I like just need to know that. Like which is like divide by T1, right? Like U1 by T1.
T1.
Like U1 is the TRV.
Yes.
The same thing I've done it. Like I'm just going to differentiate it like something like that. So if you
Why
just
that time constant is 0.001?
yeah, so this is time constant. If you just would say differentiate or just divide by the TRV to a time, then
Yes.
you'll get triple RV. So that is the basic formula, right?
Yes.
And
Yes. That's
I'm
right.
going to measure it. That's it. The same thing what we have done here.
Yes.
So this is for just for measuring purpose. Like in the output file, you can see what is the triple RV and what is the fault current. So just for measuring purpose, we are using this. And
Yes.
this is important. Like you should able to see all three phase independent RRV and triple RV. Like sorry, triple RV and TRV. For the
Yeah.
A phase, you should have independent or a separate graph.
Yes.
So for the C phase, for the B phase, we did the same thing. So any doubts on this part, like how this block is done?
No, the only thing is, see the time you are dividing that
Mhm.
at the end.
Mhm.
What exactly is that time? How you choose that much zeros, or what's the logic behind it? Time constant.
This is microsecond, right?
Okay,
Triple RV
so
by
that's just
micro.
that's
KV
just a
by
1 microsecond.
yes, KV per microsecond is a triple RV. So
Okay,
I'll get
so
the KV from I'll get
yes,
the
from yeah
KV from
from
TRV.
from the calculation, yes, and then you are dividing by microsecond.
Yes,
Okay,
exactly. So the
yeah,
triple RV.
that value only I was asking. Like, how do you
Fine,
reach
fine.
that 0.0001?
So like KV per microsecond. So that is the basic like the formula or basic definition for triple RV.
Yes, this is much based
So
on the
any
control system, PSCAD.
yes. So but like this is very basic for TRV. Like, it is,
Yes, yes, I understood the functions and this multi-run and everything, because this is pretty much we are using already in elsewhere, like in FFO and VFO. So yes, yes, I understood it, like how
okay.
it's working. I need to memorize it though, because it's too much to understand.
Hmm.
To keep in the memory, I mean.
Okay. And one small thing is in TRV block. Like this
Yes,
is you have to get the object file. Like if you just for example, this is the file which, for example, if I'm sending this file, what you
yes,
have to do is you have to just right click. You have to go to project settings.
yes,
Here you can see a link, right?
yes.
This is additional library or object file. This is an object file, like the TRV block is an object file. This is not from the master library.
Yeah, so I need to refer
So,
that, but yes.
yeah, so you have to get it from there. Like there is an we have get it from the PSCAD webinar. Like I'll just show you that file.
But you said in the new version, it is not like that, so I don't need
Uh,
to do the referencing,
in
right?
new version, there is no need for that.
Okay. Why I am saying is because in the new version, I try to link that file for something else
Mhm.
uh, using their PowerPoint or something. I don't know which case was that, but this link options is no more there in version 5.
Yes, because like lot of things have been in the master library itself, so
Yes.
there is no need for such things.
Okay.
So this
Yeah,
is
version 5 came up with quite a lot of options with respect to TRV, and
Yes.
means what to say, you can set everything, and that itself will say like whether it meets the requirement or not. So all the standards and this thing that's the real reason why they have had a major revision. Like 5 previously they used to come with 4.3, 4.4, 4.5, 4.6. Now it is major revision, and even they
Yes.
have increased the price. But like means what say, transient and all means this TRV in a version 4.6, like you have to spend quite a lot of time. But in 5, I guess that's means everything is a ready-made block. You need not really.
Yes. I noticed one thing. If you try to save something using version 5, it does not recognize in version 4. It says save in version 4, so you need to go save as version 4, and that's how you can open that in version 4.
Right, yes.
so you have to link this object file. So to link that
Yes.
object file, you need this file. Like this is from the webinar, like the PSK knowledge base. If you just double click it, you can see the object file.
Yes.
So GF42. So that's
Yes.
a photon, like that's a photon I'm going to use.
Yeah.
So if you double click, you can you should take this value.
Okay.
First step, what you have to do is you have to this is the file. For example, I'm sending this file. What you have to do, you have to just right click. You have to give project settings. Then you have to go to link. Then you have to just delete this. Then you have to go to this browse. Then like for example, I have in my download list, so I can take this value and I have to take this object value. Then like objects, then the GF42, then the TRV code. That's it.
This is only if I want to use that particular block.
Exactly. So if you're like in TRV, we will be using this block. Like without this block, there is no TRV. So
but in old version only, is that right?
Yeah, only in 4.5, not in above 4.5. Only in 4.5, it's something like this.
I can copy this. I can put it to one of my paths, and I can locate it using that link options, and I can run the case.
Yes, exactly. Yes.
Okay, it's clear. Yes.
I'll just show you how the plot will look like. Just give me some. Just a minute. I'll just show you that.
No problem. No problem.
Zero TRV. Okay. Final report. TRV. So this is the plot you'll get. Like for here, you'll get something like this. Like in this plot, you'll get something like this. Like the here, this is envelope A and this is envelope. This is TRVA. Like
Yes.
you'll get a plot something like this. So this is the envelope.
Yep, for the TRV.
And this is the TRV. If you just go into this envelope, here you can see all the T10, T60, T90 values. I don't know to show that. Fine, I'll just show you that.
Is it possible you can disable that multi-run and you can run the last?
I have done it. I have done it. Like I just show you that. So here, can you see it? These are the T10 and T10 values. Like I'll just disable this. I'm sorry. Yeah. For example, the T10 value is 787. This is 400 kb, and T10 value is 787.
Yes.
So first I have to choose this value 687. Like the T10 is 687. So this is a tick mark, right? Like then I can only see this T30.
Yes. And
below I have to click this and I have to check whether it shows 687. That's also a T30 value.
Yes.
And I have to click this. If I'm not going to click this, then you can't see the like the lower envelope.
Yes.
So for example, for instance, like I can show you that. Like here we are getting 14.82, right? This is on fault current percentage.
Yes.
Then I have to compare with T30.
Yes.
I'll just go into envelope. I'll just enable this two option and I'll check it. I'll just give it. I'll check it. Okay, this 687 is T30. Then on the lower envelope also I have to check it whether it's in 687.
And then you also need to check your plot.
Yeah. Then I have to check in my plot and I can just what is the over voltage that's going to occur. So that's the same thing I have given here. The same thing.
If it is within this these two boundaries, everything is okay. If it's not, then there is an over voltage.
Yeah, there is an over voltage. You have to tell that. Like here, the limit is around 700, but our like here you will get only 330, 397.
Yes.
So this is how, like for the A phase you have to show something like this. For the B phase and for the C phase, you have to check all the three phases, and all the three phases that should be the over voltage should be within the within the envelope.
Capability.
Yes, exactly, capability.
And then when you do this TRV for say for one breaker, how many breaker you can do this, like for all of the breaker, or based on again like some judgment?
Yeah, no. Like you will be defining some cases, like based on the your system.
Current.
You have a cable or you have a transmission line, you have a transformer. You have to define a cases, and if there is a fault on the OHL, you know that, right? So, for
Yes.
example, if there is a fault on this line,
Yes.
like you will be tripping
No,
only one of the circuit.
my question is like in this particular bay, if there are 3 breaker, how many breaker you need to see? Just one in one bay? Of course, you will decide based on, like you explained in the beginning, based on it's connected to the overhead line, or it's connected to cable, or it's connected to both of them, you know. But the question is, in a particular bay, when there is an incomer from overhead line, there are 3 breaker. How many breaker you need to check?
For example, you will be opening this 2 breaker.
Yes.
And you have to check what is the worst case. In this breaker, you have to check the fault current.
Okay.
And in this breaker, you have to check the fault current. In both of the
you need to run both.
Yeah, just check the fault current, not the TRB.
Yes, just fault current. Yes.
Yeah, just you can measure an ammeter over here and you can check it. Or inside the circuit breaker itself, you can check the current, right?
Fault current, yes.
Just check the fault current. Out of which has the higher fault current, you can take that. You can measure the. You can take that component. Like you can just drag this. You can just drag this, and you can just paste it over here, and you can just do the TRV.
Okay, I get it now.
Yeah. So this is again RRV.
Yes.
So this is how, like for the RRV also you have to show it in for A phase, B phase, and C phase. Right.
And RRV is just a rate. So as long as this is in capability curve, the first one, it doesn't matter then.
Yeah.
Right.
The RRV also some limit for that. Like this is the limit. 2, 3, 5, and 7. If the fault current is like it is T100, then the limit is 2. But in our case, it's T30, right?
Yes.
So the limit is 5 kV per microsecond.
So will it be possible that the first curve is within the capability curve, the first TRV, and this RRV is exceeding? It won't happen, right?
I never seen such
There
condition.
is a possibility. There is a possibility. Like means what say when you are chopping the current, this may happen.
Okay.
So means what to say, like when there is a current chopping happens. Okay, so the current is brought down to 0 instantly, and then like means what say that has to be reflected as a voltage. So the speed at which the RRV rises is means what say there is a possibility.
Okay.
And RRV, I mean, so say your question like RRV is within, TRV is within the limit. Is there any possibility that RRV is
exceeding?
Exceeding? The answer is yes. That there is also possibility for that. It is not necessary that like means what to say this one, and probably means what to say if you assist. It all depends upon the system. So TRV says like what is the voltage across the breaker when the breaker is opening.
Yes.
RRV says like means what's the rate at which it is increasing.
Yes.
Okay. So the rate at which increasing is probably proportional to the speed at which you brought the current to 0. Like means if it is opens at 0, then probably means what say that may not be the case. But when you are chopping the current, then probably yes, RRV could be means exceeds, whereas TRV is still within the limit.
Okay. I get it. And then again, because these values are like coming off the standard, so again you can mention like, okay, the TRV is within the limit, however the rate exceeds the values.
Correct, yes.
Okay. Yes.
So this is how you model in PSCAD, like how you model. So do you have any doubts up to this, like for the modeling part?
No doubt on the modeling part, as I said, is like I need to grasp it, and it will take some time for me to do that, to memorize.
I guess like that takes quite a lot of time. Means probably only when you start modeling it, probably it takes then you can understand. But do you have this version 5 PSCAD in your office?
Yes. No, not yet. I have been told like it's coming, but it's 3 weeks now, and the IT takes forever. as I said, is there is one IT, then is soft IT and hard IT, and then is digital IT and non-digital IT, and so I don't know where is that, because I checked with my line manager.
Uh-huh.
So line manager is not like necessarily your like technical head, but it's a kind of your day-to-day basis HR responsibility and who can take decision for you. So I asked him what's happening with this PS CAD buying. So for last 3 weeks, he's saying he sent proposal and it's with IT and he's changing. So no idea on where it. But we are buying it. It's 100% and it is in like procurement phase with IT. That's what I've been told. So it will take some, I think, maybe another week after.
Yeah.
Yeah. And now it is coming with a certificate license. I heard that they are opting for a certificate license where it is like a network license and not a dongle based license like CDAC.
Yeah, it's a network license. Like means if they have a login, like anybody can log in from anywhere in the world.
Yes, that
So
is
only,
good. That is good.
That's right. Yeah. But the only problem is like means what to say. Someone probably means what to say. Engage it, and probably means if they fail to return the license, then probably the second person in the remote may not be able to open. That's
Yes,
only.
yes. Yeah, so end of the day, you need to make sure that you say end license and
Correct.
return license.
Correct.
Yes. Yes, but I have that another version, and I when I learn something from here, if I can run that small module in the here like in my office laptop, I do that. Otherwise, I open my personal laptop and I run it there.
Okay.
Yes.
Yeah, maybe Gokul, like let me take maybe another 30 minutes for like means what say some key points which you need to make a note in the TRV. Okay. So then probably means what's left out with that, like you can go ahead. Let me take maybe next 30 minutes for that
Thanks, sir.
TRV. Right. So I will probably means what to say open that like last week we have opened some main master. No, I'll just open that and I'll just start. Just give me a second.
No problem.
Connectivities or yeah, I'm sharing this.
Yes.
Right. This is what like means what's originally like I have used, correct? No, like
Yes.
TOV, FFO, VFFO, row resonance, and TRV. Like means what say from perspective of equipments. Let's talk about this bit more. So
Yes.
TRV. So means our mindset or conventional understanding might be like means what say TRV will be more when the fault current is high, but answer is not so. Okay. So worst case is, let me zoom it a bit more so that it makes sense. Worst case for a source is not the maximum fault current.
Yes.
So what I mean, like means what say, if you have a fault current of I mean what say the system short circuit level is like 63 kiloamps, but your actual fault current is like 40 kiloamps. Means what to say, if you run for a 40 kiloamps, that is more than sufficient. You need not really run for a 63 kiloamps. That's the rated short circuit current, because 40 kiloamps is the worst case, not 63 kiloamps is.
Yes, I have a question on that. Like when you are saying the rated current of circuit breaker, I know it comes from a standardization committee, right?
Yeah.
But what that current is 63 kiloampere is phase to earth fault current or is 3-phase current or what it is? I use that current a lot for like equipment, conductor sizing and all.
Correct.
But I don't do that much here, but I have used it before. But what it is, and I don't know that.
So means what say, if the fault current in all the 3 phases is this much, like if there is a fault in a single phase, it can go only that current in that particular phase. But if it is a 3-phase fault, this can go in all the 3 phases in the same current. and your equipment has a capability to withstand, that is a short time withstand rating, and your breaker has a withstand and breaking capability for that fault current.
So that is both current. It can be maximum 3-phase and maximum single phase.
Yes.
Okay.
Right. So what I am trying to say, when you are running a TRV, the worst case may not happen in the maximum fault current. That may happen in the minimum fault current. So like I mean, what to say, but that impact is not really much. The impact is something really different. Like means what to say, means what to say, how do you visualize like 63 kilometers fault current, 43 kilometers fault current, 20 kilometers fault current, and 2 kilometers fault current in a real system? Like 400 kV bus is there. So I am giving a fault current as like 63 kilometers. Actual fault current itself I am giving as a 63. In other case I am giving 40. Other case I am giving 20. Other case I am giving just 2 kilometers. How do you visualize it? So how do I visualize what I am trying to say? Like means what to say? If quite a lot of generators are connected, and only with the generator step up transformers, and means what to say, not much of length of a transmission line, then the fault current will be more. You got the point, no? Like means what say the impedance is means what say otherwise like means what say we can easily relate like impedance. So impedance is inversely proportional to the short circuit current, correct? No?
Yes.
So like let me open an Excel sheet also. Yes, I have it. Something. Yeah, okay. Yes. So means what I'm saying like fault current I. So this is like 63 kiloamps, like 40 kiloamps. I'm just taking some example 2 kiloamps. The voltage is 400 kV. So means what to say, then like means what to say, this into 400 kV, that is voltage into 1.732, that probably gives the short circuit MVA, correct? No, this is short circuit current.
Yes.
This is short circuit MVA, right? So I can just fill it. And probably means what to say, if I put it, means what to say, is it in per unit on like say example 100 MVA base, just for my easiness, everywhere we consider like means what to say 100 divided by this number gives what's the impedance, correct? No? So means what say this is the means what say source impedance which we are thinking, correct? So what does this mean? The source impedance is quite less. What does it mean? This means more current, and this means like means what say multiple parallel paths are available from the source, and that has means what say when multiple impedances are in parallel, then the impedance will come down. That's the reason why it's a small value, correct? No?
Yes.
So means what say this could be interpreted like means what to say there are many parallel source that could be like a generator transformer and connecting to a common bus, or probably even if it is connected with a transmission line. Okay. But when it comes to here and here, and when we are going higher and higher the impedance, what does that mean? Like means what to say means one way the short circuit level come down because of the length in transmission line, and second one it's also happens because of the source itself less. You got the point, no? Like means what I'm comparing the fault current of 2 kiloamps can happen for two reasons. One is a weak grid. What I mean by the weak grid, so this grid is entirely fed by only renewables like wind, solar, etc., etc. There is no strong synchronous machines which are available to create a fault current. That's a weak grid, correct? No?
Yes.
The grid itself weak. On the other side, it can happen in a strong grid also, but probably means what to say there is a long transmission line which is a radial line which is going to a remote place.
With a huge impedance.
Yes. So means what say the line length is high, and probably means what say the impedance is higher. So means why I am trying to stress or differentiate this because means what say where the TRV goes, where the TRV doesn't go. That's what we need to understand. Strong grid with the long transmission line, or probably a radial system, right? So then probably means what say when we compare this, TRV will be worse here. TRV will be worse here actually. But whereas I mean what say strong with the long transmission line, if you go in a radial system, yes, I do agree there is a inductance which is increased, but this transmission line have a sufficient capacitance also. You got the point now here, like only the R and L is high, but the capacitance is less. Here it is just not R and L is high, the capacitance is also more. Yeah. You got the point. So the TRV will be means for say very high here, but TRV will not be high here. So probably means for say when someone gives 2 kiloamps, you should not just like that conclude something where like means what say
okay, 2 kilometers, that will be the worst case. No. So what I'm trying to say, apart from
It will
this,
depend on the system.
correct. So 63 kilograms or 40 kilograms or 20 kilograms or 2 kilograms, like we model is just a simple resistance and inductance, and we will just give it connected there. But one thing which we, I mean, so to say, not really add with the source is a capacitance what is available, unfortunately, but that plays a tremendous role with respect to TRV. So means what logically we need to check is whether we have a less short circuit current because of a long transmission line, or we have a weak system, so the short circuit current is less. So it means if we have only 2 machines or 3 machines like 180 megawatt or 200 megawatt demand isolated systems, then obviously the system strength itself less, and even I mean what to say the impedance is more, but the capacitance is less. You are able to visualize the system, right? What's the two different systems which I am telling? So one system is connected with quite a lot of sources. There is a fault current higher, but just because of the transmission line length, the fault current is coming down. Like if you take the 400 kV line, means what's typically if you take like a 300 kilometer line, the fault current will come down means what's say from 40 kilometers to maybe 2 kilometers. Maybe you can probably means what's say put it in PSCAD also to just simulate this. I can probably means what say just quickly simulating this in ETA means because the time is less where there you need to model transmission lines and other stuffs. So just give me a second, like.
No worries.
Yes, it will take a lot of time. Means you also, means what say consider the same scenario for your earthing or for your substations also, correct? No, means what say if the substation is close to the source or means far away from the source, correct?
Yes, we calculate that ground return current, and I also do the method you were saying, the parallel path. In India, it doesn't work in that concept, but here it does work. So if my MAT value is say 2 ohm, 5 ohm, 10 ohm of substation resistance, so when it comes on the impedance, as long as that substation is connected to the various overhead lines, then we don't treat that impedance or resistance as a high, because it is going to decrease down because of various parallel paths of overhead line tower footing, and we call that as a overhead line chain impedance.
Yeah. Okay.
So if the substation itself is say 10 ohm, and there are like transmission line other side 30 kilometer as well, and there are so many tower footing connected to that 10 ohm 10 ohm 10 ohm as a standard value. So if we parallel substation plus those all tower on either side, so that impedance will not be 10 ohm no more, it will be like 0.01 ohm and an angle of like 30 36, something like that. So that's what it's called, is a concept of chain impedance.
Right. So just give me a second, like means what say I'm just trying to means what say showcase like why this fault current could be less in a 400 kV system. That could be for two reasons. So this is a means what say sincere factor, probably means which needs more attention, but unfortunately this engineers, those who are not really coming from the system study background, may not be able to understand this. So
Okay.
yes, and that's what happening. So I mean what say, let me create a fault at both the buses.
You can create a transmission line here. Nice.
Yeah, this is a transmission line. Okay,
I thought you can only create like pi section and all those things.
Yeah, this is a transmission line model. Like means what say, I can select the phase conductor, I can select the ground wire, I can give a configuration. Then probably means automatically this finds out the means what say resistance, inductance, and capacitance parameter. And in fact, like means this also probably means what say like transposition configuration is also possible. Like you can put like a transposition, and then probably means what say you can look at this matrix becomes like means what say you can understand,
and
right?
For what study you model a transmission like this in ETA?
Yeah, it actually means you anyway need resistance, reactance, and capacitance. No, so there are two ways of doing this RX values. So one, if the customer gives this value directly, we go with user defined and we fill this value directly.
Yeah.
If not, like means what say we'll get the configuration of the tower and probably means get this conductor parameters and we will calculate this.
Nice. I thought you can only do like some these RXB base and input here, not like this
Okay.
transmission line as a whole.
So means what say if we run a short circuit, you can understand. Means what say I will display the line parameters also. The fault current here is 40 coulombs because I have given that as a 40 coulombs, but like just for a length of means what say 300 kilometer. So means the fault current has drastically came down.
Yes.
Right now I can plot this impedance as well. Right, means what say the fault current came down from 40 coulombs to 2 coulombs. Correct, no?
Yes.
And
Yes.
you can understand means what say you call the system as a weak system, but this
Yes.
is a weak system, but with a huge capacitance in front of it. Correct, no?
Yes.
So means what
Yes.
say this capacitance is there, but probably means what say we take another system, like assume that that's a like means what's only generator and probably means what's the other side there is no other sources which are available. Assume that this is the only generator which is available in the system, and probably means let's connect it to this. Right now, let's create this is like a 400 kV.
Yes.
Probably I'm just giving some transformer ratings. 28 kV is the generator, maybe 960 MVA. Like 800 megawatt. Assume that like some kind of thermal plant or something. So now if I go back and probably means what's a simulate a case with a fault here as well. Yeah, here if you look at like means what's a here 2.129 kiloamps, here it is 4.3 kiloamps. So means what's a this system we call it as a weak system. This system is comparatively means what's a better than this, correct, no?
Yes.
But means what say here means what say we will get the worst case results for this 4.8 kiloamps, because say example I'm putting a breaker here. This is a high voltage circuit breaker. Yeah. If there is a fault in bus 4, then circuit breaker 1 interrupts the fault current. But
Yes.
when it interrupts the fault current, it is probably purely means what's breaking an inductive current. Correct? No, this X by R is also higher, and this X by R ratio of the transformer is also extremely higher, and there is no capacitance there. There is no capacitance there. But here, but if you look at here, like means what there is a huge capacitance is there. Like means what then the capacitance offsets the TRV, and hence you will not have any huge problem with this.
Yes.
But on the like means what let's probably means what look at the other scenario as well. Like means what with the different lengths. So I mean, intentionally we change the length to 30 kilometer, and then probably maybe just keep it as 3 kilometer. So the fault current is again means what say here it will differ. Right here it is 14 kiloamps, here it is 33 kiloamps. Yeah, so means here you can understand like means what say even here means the fault current is only 14 kiloamps, but the 30 kilometer capacitance value is present there. Correct?
Yes.
No? Even if you take here a 40 kiloamps, like what we are assuming means one generator cannot really give a 40 kiloamps there. Correct? No, means what say it is like multiple generators connected to this point or multiple transmission lines connected to this point. But means what say you cannot really connect like means what to say multiple generators to means what say increase this short circuit level. Like means what say if you understand like one plant of 800 megawatt is able to contribute only 5 kiloamps. Like means at max you can see means what's a 4,000 megawatt as single plant, like not 10,000 or 20,000 megawatts. Correct? No, because that 20,000 megawatt cannot be extracted at 400 kV level at all. At max you can go with the only 4,000 megawatt. Correct? No.
Yeah.
So the fault current can happen at this bus can be maximum of 20 kiloamps that could be contributed from the generators. That could be contributed from the generators. But otherwise, like means what to say, means when you have multiple transmission lines here, like means if the substation is connected with the, like 20 substations, like what you have shown in your this one of the document, like then that means that it is a heavily interconnected system. By the time also the fault current will be more. But when the fault current is more, still the capacitance is also more. So there will not be any problem with the TRV. So the TRV requirements when you are looking at, so look at the TRV requirements and triple RV requirements for your normal breakers, and look at specifically for your generator circuit breaker. So you may be aware, like there are some circuit breakers which are directly connected here, and there is means generator circuit breakers, right? So means if you have the circuit breaker here, and this TRV requirements is not really covered under IEC 62271. So like there is a dedicated standard for that generator circuit breakers, because the generator behavior is completely different. So it's not really IEC 62271. So then probably means you need to do an extremely different model and completely dynamic model of this generators, etc. So what I'm trying to say, whatever the TRV we have seen is applicable only for a conventional substations, not really for a generator circuit breaker applications. And generator circuit breaker applications, like means you might handle, like means Google it with this one, like you will get infinite papers on the generator circuit breaker TRV. So means many documents will be available, and that means what say modeling of the generator is at most important when it comes to such as generator circuit breaker applications. And one more thing, like means what say you may be connecting means what say multiple generators together in a, like means what say if it is a small plant, like means what you will do, you will means what say in the medium voltage itself, like something like 11 kV. What you will do, you will connect multiple generators of small capacity, and then you use a common step-up transformer. Correct? So like maybe say 8 megawatt or 10 megawatt. So means I'm not really giving any parameters, like just to understand like how the system, and probably means for say you might be connecting maybe 4 generators or 2 generators, and it is connected to a common bus. And then you will be having a common step-up transformer to step up to maybe 110 kV or something. So in this case, like means also you will be having a breaker everywhere.
Yes. Interrupted generator. Yes.
Everywhere. People think like means also that breaker duty will be stringent, but the means what say the breaker duty faced by the auxiliary transformer, which is connected to 415 volt, like if we assume it's a diesel generator or something, you may need some auxiliary power, like means you will be having like 400 system or something. And this breaker, the fault, when there is a fault here immediately after the breaker on the transformer HV terminal, the fault current interruption will be extremely difficult for the circuit breaker, and that TRV will be much worse, because that has to interrupt the fault current not only from all the 4 generators but also from the transformer which is coming. So the fault current interrupted by this circuit breaker is highest among all this breakers, and the TRV requirements for this circuit breaker is much more stringent than all other circuit breakers. So means these are some common things which probably we may miss. Like means people always think that this breaker is connected to generator, so means that is means what's the most stringent requirement, etc. But here, like if you look at means in this direction, means if there is a fault in this bus, the circuit breaker 6 is just breaking only the fault current from one generator. That's all.
Yes.
And if there is a fault here, means this circuit breaker has to break the current from transformer plus these 3 generators if it is running.
Yes.
That's applicable for all the faults in anywhere in this place. Correct? No?
Yes.
And that's very critical. Like here, it is generator. This transformer grid contribution plus all the 4 generators. So fault at this transformer HV terminal is more stringent than any other cases.
Yes.
Yeah, right. So means what is it? Then one important dimension of what we need to really look into is what's the fault current which we are considering, and whether that fault current is coming from transmission lines or probably from a source like a generator, because this fault current contribution and this contribution is completely different.
Different.
When this is fed by multiple transmission lines, then that means that has a significant capacitance, so that plays a significant role. But whereas if it is something like this, then this really doesn't have any significance. So that's what we need to look at.
Yes.
Right. Okay. And Google, can you just open your model, Google, and share it? Like
yes.
You had some seminar today. I was saying somebody was saying it was some 5:30 a.m. in my time, so that's 9 o'clock today.
Yeah, 10 o'clock I had.
Yeah.
That is okay. That is Ask Selva what I do in YouTube on every Sunday 10 a.m.
Every Sunday. Wow. Your wife is happy with that? Every Sunday, like I am doing this Sunday, my wife is going mental. She's like, what you are trying to do? What are you trying to do in like your personal time? And like, well, it's all right. So if I do like every Sunday, I just say like, oh yes, for a few months, you know. Happy wife, happy life.
Okay. So here, I mean, what's this remote substation like RAF Super and Salia Super, correct? No, this two substations. Yes. Like here, you need to. I mean, what's say? Can you just go and see how it is modeled, Gokul?
That is 3 cable.
Yes, sorry. That's all. Means I'm looking at how it is modeled as a source.
Yes.
Yeah. Source. Yeah. Go inside, Gokul. Yeah, it is plainly modeled as a. I mean, what to say? Voltage source. Correct, no? Yes. It is not modeled as an infinite bus. It's not modeled really as an infinite bus, but it is modeled with only the R plus JX.
Yes.
Correct, no? Can you just go inside the short circuit level and show this? No? Yeah. So you have given positive sequence impedance and zero sequence impedance. That's it. That means what you have modeled is literally a voltage source with the R plus JX in series. But in reality, means what's it, that could be coming from n number of transmission lines, similar to the cable and transmission line what we have in our substation. This line also will have quite a lot of transmission lines and etc. There is no real voltage source which is connected on the other side, correct? No.
Exactly. Yeah.
So what I'm trying, what we are trying to say then, because of this model, what's the key parameter which we have missed is what's the capacitance in shunt at that particular place.
Yes.
That is the key parameter for a TRV. So that's the real reason why, means when you're performing a TRV study, you have to model at least 2 substation levels away from your substation.
Okay.
What you got the point? No, like means this substation you should not put a model as a source. From here where a transmission line or cable is going, there you have to connect, and probably from there you have to model as a voltage source. At least that gives like a capacitance of means what's say 2 levels of substation. That is also not really right, but at least means what's say comparatively that gives a better results or more realistic results than like only one level we are going. But getting this data from utility again, that's all. Probably means what's it's extremely difficult. Yeah.
Yes.
So that's the one. I mean, what's the important fact? Rather than modeling a small capacitance in your substation, like means what say Gokul has explained. Can you just go to our substation? No? Yeah. Yes. So here, when you are looking at like you have model a CT, you have model a VT, like etc. 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 But these are all in picofarad, correct? No.
Yes.
That's hardly nothing. It's but your transmission line capacitance is in means what say microfarad, correct? No.
Yes.
So even 1 kilometer length of your line, which is adding on the upstream, has a huge significance than compared to all of the small capacitance, correct?
Exactly.
So that probably means what say has to be properly captured. That's the one means key thing which we need to just really look into. Yes. Then second one means what say what is more interesting point which we need to really look at is this TRV is not a static parameter like what is stated in the standard. Correct, no? Means what say my dielectric strength of the breaker will increase when the contacts start separating.
Yes.
Correct. So, I mean, you have asked a question, probably means what is more close to that, but you have not really asked something like means what say you have asked when TRV is within the limit, triple RV whether it will be within the limit or not. Means
Yes.
the question can be in the other way lined also. Is there any possibility that TRV is within the limit in the first maximum point, and is it possible that second or third place it can cross the limit? Yeah. So I mean answer no, because like means what say when the contact starts separates, then probably means what say this dielectric strength of this material also will increase. Correct, no?
Right.
So the probability of I mean what say modeling that is I mean what to say means not covered under part of TRV. So means what is the study which we are doing? Like we have not really modeled the property of the dielectric strength of the breaker in detail. Correct, no? We have just modeled the breaker as a switch, and probably I mean what to say along with the parallel capacitance. That's all. Correct, no? But
Yes.
in reality, like means what say when the breaker means what say starts breaking its contacts, like then the dielectric strength will increase. So if you want to study the restrike, means what say let me take. Can you just go to the reactor portion?
Yes, sir.
Yeah. So means what say the reactor is connected in the cable, correct, no? So means what say that can you just show in the upstream, Gokul? Yeah. Like means what say there are 3 breakers, correct, no? There are 3 breakers. One is the cable which is coming from RAH super, correct, no? Yeah.
And 2 are
come
there.
down. Yeah, it's coming here and it is connected to this left side. Correct. No, it is for that. Along with that, it's connected. I mean, the cable, because cable length is higher and it injects a huge reactive power. So we have put up a shunt reactor to mitigate the Ferranti effect or consume the reactive power. Correct. No.
Yes.
But if you look at means what say this reactor can be converted into bus reactor also. Though it is meant for the cable, but it can be converted into a bus reactor also. How? I will show that. Can you just slightly go up, Gokul? Yeah. So here you can see the disconnector in the cable feeder can be kept off, and you can close the breaker which is there connected to this reactor alone.
Yes.
You got the point. No, means was a cable, it is only a disconnector, but keeping the disconnector open, still you can close this breaker so that like this means what say reactor can be connected to a bus also.
Yes.
So that's the real flexibility which they have given. So though they call it as like an on and off breaker scheme, but it's not really an on and off breaker scheme with respect to at least this place.
Yes.
Correct. Now what is on and off breaker scheme? Like you have 2 feeders and 3 breakers. So like 3 divided by 2, it is on and off breaker. But here like means also you have 3 breakers. Sorry, you have like 4 breakers and you have 3 equipment, something like that. Correct, no? So it cannot be like called as like on and off breaker scheme. Okay. Now means what's the point which I'm trying to say? Like, can you just open this breaker? Go to the reactor breaker. Yeah, that breaker. Like means what I'm trying to say. Yeah, no need to. You can go back to the main place itself. Yeah, what I'm trying to say means what say this breaker start opening. The breaker starts opening. Correct, no?
Yeah.
Means what say assume that I'm just given a normal open or there is a fault in the reactor and I'm just trying to open this breaker. So there is a voltage on the reactor side as well as there is a voltage on the source side.
Yeah.
Correct, no? So now means what is the voltage between this breaker? That is TRV. Correct, no?
Yes.
And because like means also assumes such a worst case like means also the voltage could be 2 per unit. Correct, no? Means what say 1 per unit voltage on the source side and 1 per unit voltage on the load side, but both are in opposite this one. Then you will reach TRV. Means 2 per unit voltage TRV. Correct, no?
Yes.
That is like 400 bar root 3 into root 2 into 2. Correct, no?
Yep.
Right. Now assume that like means what to say the breaker starts its opening its contact. The dielectric strength of the material inside the breaker is not really able to quench the arc.
Okay.
Then what will happen? Like means what say when the breaker contact separates, like it's restrikes, right?
Yes.
To model that, you have to model this breaker in detail with some ABCD parameters. Like means I'm just trying to say what we have not covered as a part of this. Okay, that's what I'm trying to say. So means you have to model as a part of ABCD parameters And means what's it, for that such a parameters you have to obtain from the manufacturer only, or that model or study has to be performed by OEM rather than the consultants.
Yes.
And then like means what's it, when the breaker restrikes, what will happen? There is already a voltage which is there in the reactor, and when restrikes, there is an additional voltage which is pumped to the reactor. Correct? No. So like assume like 1 per unit voltage is already there in the reactor, and means now you are adding a means one more strike. So this adds maybe if not 1 per unit, at least it adds some more per unit to the existing voltage. And again, means what's it, breaker will try to attempt to open, and probably if it is 2 strikes, restrikes or 3 restrikes, then means what's it, the voltage on the reactor side or load side which is extremely high, and probably means what's it, your breaker will not be able to interrupt that fault current at all.
Yes.
You got the point of the breaker completely fails. But still then, I mean, what's it, despite of that breaker is getting damaged, means what's it, you may need to safeguard your equipment which is a reactor. Correct? No? Even if the breaker goes, like okay, I will replace that breaker with some cost. Correct? No? But if it's reactor is extremely expensive. Correct? No?
Yep.
So to avoid that, like means what's it, you may need a surge arrestor or a surge suppressor at reactor terminal.
Yeah, if it goes beyond that value.
Yes. So, but means what to say? Without a restrike, your surge arrestor at a reactor terminal is not going to help you in reducing TRV.
Yes.
Means your surge arrestor will try to reduce the voltage only when the voltage goes beyond like 1.6 per unit or something. Means yesterday or the day before yesterday, I'm not really sure when we have seen that. Like means what say, we have seen the VA characteristics of the breaker. Correct? No.
Yes.
You might be aware, like Venkat or someone has taken, like means what say, what is maximum continuous over voltage, what is 1 second, what is 10 seconds, what's the value, how much current goes. Correct?
Yes.
Yeah. If you look at that, like means what to say, the behavior of the surge arrestor is trying to come into the point effectively when the voltage is going beyond 1.6 per unit.
Yes.
Okay, so means what say 1.6 per unit on the one side plus 1 per unit on the other side, like 2.6 per unit means what say means TRV that itself more than sufficient to damage the equipments. Correct? No, but like that's not really going to help you with respect to this surge arrestor. So means what you need to really look at, surge arrestor may help you to at least prevent the damage of the end equipment even if the breaker fails.
Yes.
So that's another important aspect which you need to look at when it comes to the studies.
But in general, the only mitigation for this TRV is rate the breaker higher.
Okay, just give a second. I will open up a presentation what we have made. Okay, just give a second.
I mean, like for lightning and switching, we are saying like we need to put surge arrestor to dissipate that voltage. So on the same note, I am asking like what will be our general?
Right. That's right. It's a good question. Yeah. Hope you are able to see the screen, right?
Not yet. No, it's not visible.
Not visible.
It's not. I mean, you're not sharing. We can only see a normal screen, like a call screen.
Okay, my presentation is being entered by someone. Okay. Are you able to see now?
It's loading in. Yes, I can see it. Yes.
So like I mean, for say VFFO TRV and probably means for say just we have presented this another network like the same project what you are doing. You might be aware like this another project.
Yes.
So means what say ferro resonance etc. Okay. I'll come to this ferro resonance little later. Like VFFO, it is within the limit, right? So means what say TRV is like this is what the results like where it is exceeds, correct? No.
Yes.
So means what say like means what say that probably means what to say. What are the probable solutions? The probable solution is like means what to say. One thing is what is the TRV of the breaker is considered from the standard, correct? No, like T10, T30, T60, the value which he has given, I mean, so the standard has given, correct? No, but if you consult the manufacturer, the manufacturer will give you higher values based on the design of this breaker for the same breaker. The example in our case, the same breaker like SP3-1 means what to say, we thought that breaker is 1.3 FPC.
Yes.
That's what he has also, ABB also has written and he has given to us in the data sheets and everywhere.
Yes.
But like means when we have discussed, because we have an issue with the manufacturer, what he has told, he has only one product called SP3-1.
Okay.
So means what say he cannot make two different products with like a 1.3 FPC and 1.5 FPC, which is expensive. So instead, what he does, he manufactures one product. He means what say type test with both 1.3 as well as 1.5. And whomever asks, they will ask 1.3. He will say it's 1.3. Whomever it asks, means 1.5. He will give 1.5. So then the advantage is like means what say now means what say we thought that it is only 1.3 and we have seen like only 1.3 as FPC, but like now Gokul has given like means what say if it's 1.5 how this TRV will increase, correct? No.
Yes.
So means what say then we know very clearly that this product is 1.5 FPC.
Yes.
So like means you can find out, means you not really compare with what is there in the table of this one like IEC. You can actually means also get the right value from the manufacturer, and you can based on the FPC you can increase this TRV and you can compare that value with the actual value which is occurring.
Yes.
Right. So then probably means what you can do, you can add a capacitance to the circuit breaker.
Yes.
That's another option. And probably means also you have like a gas insulated busted, no?
Yes.
That has a small capacitance. So if you replace that by a cable, then probably means what to say. That has a huge capacitance that also reduces this TRV.
Okay.
So means what to say here, like means what to say 7 kV 235, like this are all probably for 1.3 FPC. You can very well check with what's the new value for this. Correct? No, the 624, 629, etc. When you look at this, means what say means this value can be much higher because this is for 1.3.
Yes.
If it's 1.5, this value can go like means what say 850 or means what say 900 kV as well. And it probably means what say you have another option as well. Like means what say you can put up means what to say some surge resistor across the circuit breaker also. So that's also another option which you can explore to reduce this. Right.
And you also need to check, like you are showing here for the transformer energization and all these. You also need to check your breaker for that, or you just need to check your breaker for fault only.
Yeah, I'll come to that. Like what are the cases which we have done?
Yes.
So means what say when it comes to the transient recovery voltage, like what you need to do, you need to do terminal fault, short line fault, and remote end fault for a transmission line. When it comes to the transmission line, it is 3. Like you have to create a fault immediately after your breaker. Then you understand like there is something called a short line fault. Then you have to create a fault at the means what say remote end. Like means what say if I quickly go to the single line diagram to check the circuit breaker. Say example the circuit breaker. You have to create a fault immediately at this terminal, and in an outgoing transmission line, like means what say means if the line is like 100 km, then less than 30 km you have to create a fault and you have to check. And the remote like 100 km you have to create a fault and you have to check. In all the cases, like your fault current will change. So means whether you are comparing with the T10 or T30 or T60, T100, that also will change. Yes.
Okay.
Yeah, you have some question?
No.
Okay. So means
this was the question. Where I was saying, like wherever you are using a breaker in operation, like transformer energizing or a reactor energizing, so every scenario you need to check the capability of this breaker.
Correct. So means what say with respect to transmission line or a cable, with respect to only the fault, we have seen 3, like terminal fault, short line fault, remote end fault. And probably means what say for a cables, if it's a long transmission lines, you have to check the cable energization because this cable injects a huge capacitive current. Like then probably means what say if you are opening the breaker immediately after closing the breaker, then probably that you need to check. Similarly for a transformer, you need to check transformer energization, transformer de-energization, reactor energization, reactor de-energization. So like that.
So for this going back to the SLD again, for this fault, I understand which breaker you will check, but for the transformer energization, you will only check the breaker right immediate to the transformer. Not
Correct.
like all of them.
No. I'll come to that. I will clear that out. Like means what saying? If there is a fault, if there is like means what say let me take this as a transmission line, right? Okay. So means if there is a fault here, you will not check all the breakers. You will check only this breaker and this breaker. That's all.
Okay.
Anyway, because means what say when there is a fault here in this line, only this breaker and this breaker is going to open. Correct? No.
Yeah.
So means what say for a fault here you will see only these two breakers.
Yeah.
Okay. So similarly, like means what say if you are energizing the transformer, you will not close both the breakers together to energize the transformer. Correct? No, you will close only one breaker. By default, the transformer will get energized. Correct? No.
Yes.
So means then probably either this breaker or that breaker.
Okay.
Not both. Correct? No. Similarly,
Yes.
for a reactor also, like means what's the breaker which you are means what's closing? So this breaker energization and de-energization. And if there is no breaker, then that cable and the cable and reactor will energize together and de-energize together.
Together, yes.
Yeah. So that's an easy, like means what say if you have a long cables as well as a shunt reactor, then means what say your TRV results will be easy. I mean what say much lesser. But here we have only a reactor, so that's the real reason why we have a problem with the reactor. Actually, we have I mean really in this project, like we have a problem with this reactor.
Okay.
Okay. So I guess when it comes to this here, like that's what line sort. I mean terminal fault, sort line fault, remote end fault. When it comes to the transformer, it could be fault. It's energization as well as the de-energization. Reactor also like fault. Means what say and de-energization and energization. But energization you need not really check TRV or triple RV because like means after the breaker is closed, the voltage across the two contacts is zero.
Yes.
Correct. No? So like means what say you may ask like why we have not done energization. Like energization, you need not really verify TRV or triple RV. TRV or triple RV.
Because we are now opening the breaker. Yes.
Correct. Yes. Right. So means the voltage will be there across the contacts only when you're opening the breaker.
Yes. Yes.
So this is like a means what to say with respect to TRV. And one more thing like means what to say with respect to the ferroresonance, I am not really sure like what has been discussed. I guess like they have introduced the ferroresonance. I guess like yesterday, like transformer,
Yes. Gokul shared all the model and detailed simulations.
Yeah, transformer energization, transformer de-energization. Like VT also you have to check ferroresonance, single pole, double pole, etc. And here like means what to say they ask maybe a resistor like a damping resistor to mitigate this ferroresonance. So if the ferroresonance occurs, then the mitigating mechanism is like a damping resistor.
Yeah, he showed me like how we can insert a load and kill it. Yes, if there is a case.
Right.
Yes.
Yes. So anything else to add, Gokul?
No, nothing, sir. Only in IEC they have said different cases, so we can just discuss that. That's it.
Yes. Okay.
In PS card model, we can show how to simulate short line fault and everything.
Yeah. Yes. So Himanshu, like I mean, so say, how do you want to go? Because like means you need to practice. Then only you may get the doubts in like ferroresonance and this TRV or probably VFFO.
Yes. I have a plan that in office only as I said is the PS CAD is not in, and the only project is like that solar grid connected solar that I need to do. And it again says that we need to perform a transient over voltages. It does not specify what over voltages, and I have no clue about it. So the guy who is a project manager, he basically sent some TQ to the client asking like, can they specify what specifically they need? So once they come back, then I will understand. But the point is whether I get license or not, I am going to do these cases on my own.
Okay. Right,
so I won't do like maybe like all of the cases, but I will do majority of the cases, because the key here is like I am not interested in doing this for Arcadis or someone else. I am interested to do this for like my career, So I want to understand, and I want to digest all these facts, knowledge, videos, whatever you are sharing, and this is really great. It's beyond the great actually. For the price like I paid for this training, and for the level of like detailed explanation like I am getting from you guys from real experience is really impressive.
That's a great feedback to have. Thank you.
No, honestly, because okay, I understand like you are not for example, Gokul didn't work on the PS card for 10 year or 20 year or so many things, but like I was few years back, I learned something, and with that zeal and interest, I was teaching someone. So same way the guys are teaching me, so I'm really feeling is connected, like communication, good communication, and these cases and everything. I am asking files because at the moment I am in miserable position. I can't do like these. There's only 24 hours in a day, and there are so many things I need to do. So I am not getting time, but even with this course, I am opening the file and seeing them and trying to correlate with the video like every night.
Yeah.
And I am coming with some, immediate questions. But over the time, what I will do, I will go, I will learn, I will explore, and then I will do again.
Right. Okay. Fine.
That's a plan I have, like.
Yeah.
Because that there are only limited hours in a day, and there are so many things I need to deal with, and there is a little bit office politics, like, okay, I need to like do earthing, and that's how I was hired, or I am part of earthing team and so on. And then from the top there is a like, okay, you also need to develop in the background. That's like a normal world, like you need to develop this capability in the background, but first thing, you're not giving me license. Second thing, you're not giving me time. So what is the background like? so it will always be like that, I know that. So as long as I am working here, it will be always like that. So I will do all these cases, and I am doing this project, I will work that way. Like, this is my project, and I have a I study to do TRV and everything. The modeling itself is okay. Like, okay, you need to like understand, like, there were 3-4 logic we are using in this TRV, for example. So it will take me to correlate them, how they are talking to each other. But yeah, component and putting something inside is okay. It's simple, it's not rocket science. Right. But it will take some time. That's what my
that's fine.
Yeah. No, and this training is great, by the way, very, very great.
Okay,
I wouldn't get this. I wouldn't get this training from like PSCAD or anyone else, I think, because I've been into like many training courses, or I myself gave training, so I know how they, you end up with like sales pitch and showing capability and very vague, So you guys are really giving me some, hands-on experience using real project, which is impressive.
Yes, thank you. Okay,
yes.
So means what I have worried is like, this week, we have almost covered everything except this renewables, wind and solar. That's the only thing which is pending. That's why I'm asking. Like, then more or less, like, we will wind up next week, and probably then you can practice it at any time. Like, if you have any questions or clarifications, like, we can sit maybe 2-3 hours on a weekend, then we can discuss.
Yes. My approach would be like, I will try to figure out answers on my own. Because if I immediately come to you, then again I become like dependent type, and I don't learn. Well, that's how I see. I didn't mean to be like, I don't want to bother you or something. But I will try to get answer on my own. Like, it will take days, weeks, months. So I will try to do that way. But if I need like immediate help, and I think like this is not something I am getting off the a PSCAD webinar or a standard or something, then I will come back to you, or I will ask the question.
Sure. You can even use that WhatsApp group.
But believe me, whatever you injected into me, I will return it like 200% back. I will break this software someday, soon.
Yeah. I could understand. Like, we are also extremely happy. Because we do these courses for many people, but we go only with one resource. And probably that too, probably the person who will be sitting on the opposite side, like, okay, something like that. But personally, we enjoyed the class with you also, and we have learned a lot.
This is not only about learning a software. I can, as I said, like, I can get it from like anyone else for maybe cheaper price, maybe expensive price. But it is about the value of the content, like how you are teaching, how you are treating your student. So you are really like sharing these PowerPoint, and then, for example, the bus bar scheme, you would have said like, okay, go and Google it or see YouTube, but you really put some effort to give me, and it's not again like very big thing like that I would not know, or there is no resource to learn it. Of course I can see over thing, but you are creating that atmosphere to put like everything in this training, which is really impressive, honestly. For that price, and for your effort is great, and I'm really thankful to you on this part. For the substation, I am very, very confident that if a project comes, I can do this project on my own without any problem. And
Yeah.
and the reason I am asking questions, because if you don't ask, you don't learn. That's how I believe. So whatever comes into the mind. uh, I was like good in academics, so I got good marks and everything. I remember formula, but over the year I forgot everything. I don't even remember the EMF equation of transformer or this per unit system and everything. I know like what is per unit and all those things, but it will take me a lot of time to go through these and get like the same confidence again,
Right.
based on your training. So I don't feel like shame asking. Some people feel shame in asking questions, but if you laugh at me, it's fine. It's your thinking. You laugh, fine. I will go and I will get the knowledge. That's how I think.
Great.
Some people are ashamed because they think they are on a certain job level and so much experience, and then they feel ashamed of asking questions, or they feel like if I ask this guy, what he will think about me or what she will think about me. I don't think that way. I think, okay, fine, you want to laugh, fair enough, go and do it. I don't think problem. Every day is school day. That's how I see it. Every day you learn something new.
Right.
But this course is really impressive, honestly.
Thank you.
Whatever Gokul, Venkat, and your other colleagues shared, it's really, really great.
Thank you. Yes, Gokul, you can.
Yeah. Fine, sir.
Yeah.
Only how to the cases. I just want to explain how to model it. The short line fault and the remote end fault. Like I just want to show that.
Yes, please.
I'll just share the screen. Okay. So first you have to create this fault module. Like you know how to create this, right? Like you just go to module
Yes.
and you can just create it. So first,
yes.
after creating it, you have to, for example, let me do this. So I'm going to take this cable and I'm going to do the different types of cases, which is short line case, short line case, terminal case, and a remote end case. So I'm going to
Okay.
take this breaker. Sorry, I'm going to take this breaker and I'm going to simulate that. So first step or the first thing, like let us go for an terminal fault. So a terminal or like if I just place it over here, this is a terminal fault for the circuit breaker, right?
Okay.
The fault is at the terminal of the circuit
Yes.
breaker. So this is terminal fault. The next one is remote end fault. You can just take this. Sorry. You can just like take this. You can just like Control X. Then you can go here and so you're considering this cable, right? So
Yes.
this circuit breaker you are going to do. So
That is.
you're considering this cable. So if you
Yes.
just place it here, then that is remote end fault.
Okay.
And a short line fault is somewhat like a bit tricky. Like generally that would be 30% or away from like 3 kilometer. Like that's what we used to take. I just show you
Okay.
that. If you just go into it. So this is the cable. So
Yes.
edit parameters, and this is 16 kilometer. So what
Yeah.
I'm going to do is I'm going to separate this two cable. First cable it has 3 kilometer, and the second cable is the remaining kilometer.
Okay.
So like I have just showed you that. Like first, what the thing like, for example, if you just try to copy this and you just try to paste it here, like I'll just show you. So first, if you just this is in one module, right? I've just
Yes.
like I'm going to copy this and I'm going to just paste it here.
Yes.
And sorry. So yeah. So what I have to do is I have to change this as 3 kilometer, right? Like I can
Yes.
just go to edit parameter and like I can just like give
Change
3 kilometer. Yeah. But the issue is if you just go into this, you can see the same the change. You can also see the like the same change we have done here. So
Yeah.
all these things are all these modules are one of the same. If you do any changes in one module, all this module
Yeah.
will get updated.
Updated. Yes.
So
And
what
then
you
it
have
will
to do
become wrong.
is yeah, sir, there is like a small different method for that. what you have to do, you should know what is the name of it. Like it is
Yes. Cable one.
untitled one, right? Untitled one. Like the
Title one. Yes.
component name is untitled one.
Yes.
I'll just show you that as well.
So you create from
So-
the definitions.
Yeah. So this is the project we are working on. So you just go into, like, you can see the definitions, and
Yes.
you have to search in the definitions. You have to search for untitled one.
Yes.
That will be this is the untitled one. So
Yes.
what you have to do, you have to just copy this,
Yes.
and you have to just paste it here itself. I'm sorry. You have to just copy with dependence, like copy with
Yes.
dependence, and then you
Yes.
have to paste it here. I'm trying to
Paste instance or something.
Yeah, that should be, yeah, here you have to do it. So untitled one, right click, copy with dependence,
Yes.
then
Paste.
paste definition. Yeah. So then it will ask for rename. Like for time being, I'm just going to give a different name so that I can easily identify it. So
Yeah.
cable 311 and untitled 511.
Yes.
So then if you just scroll down at the end, you can see this. You can take this module. So this is the module we need. We don't need the cable. If you just copy this, the cable will be inside this.
Yes.
I have to just right click, create instance,
Then-
and right click, and I have to just give paste.
Yes.
Then here I have, like, if I, for example, if I just try to give some, say for example, I'm just trying to give 1 kilometer.
Yes. I can get one.
So here it will not change. It should not change. Like here it is not changing.
Yes.
So if I change anything here, like it will not change because those two are different modules.
Yes.
Like for example, if I take 10 kilometers,
Yes.
you can check this, edit parameters, then you will not get changed. So this is
Yes.
important. If you are just trying to copy this and paste it here, you have to be cautious on that. So you should not change the values.
Yes.
16 kilometers. So now what I have to do is, so if I want to do a short line fault, I'll take this fault and I'll place it here. So here this is 3 kilometer and the remaining 16 kilometer will be there. Like,
And there is no logic what short length means of the full route, or there is a logic behind it, or you can just randomly select a value close to the substation, close to the the substation of interest.
that will be generally 30 percentage. 30
30%.
percentage.
Okay.
Yeah, 30 percentage. Like if you have
30% of total route length. Okay.
yes, generally 30%.
Yes. Yes.
So this is short line
Okay.
fault. If you're going to simulate, we have to simulate three kinds of fault, which is
Yes.
a remote end fault, which is the fault should be here.
Yes.
Next,
And
the
then
short line
terminal
fault, the short should be here. Then
and terminal
the terminal fault, which
right
you
next
have
to the break.
yeah, next to the break. So this is
Yes.
the break I'm going to study. So this is for a cable and everything. For the transformer, that would be different. So what you have to do is you have to
Yes.
take this fault. So you have to
Yes.
place a fault over here. At 400 kV side, there is a fault. So you have to, now you are going to study two breakers, which is 400 kV side will also like open, and 220 kV side also will open, right?
Yes.
Yeah. So what we have to do is you have to study, you are going to study two breakers, right? While
Say
doing
that.
a transformer
Say this
case,
again.
yeah. If you're going to simulate a cases in transformer, the first thing is
Yes.
you have to model the complete system, the 220 kV side also.
Okay.
Yeah. Then two breakers you will be opening, right? If there is a fault or 4 like 400 kV, the 220
Yes.
kV side breaker also will close. Like you have to consider the 220
Yeah.
kV breaker also.
Yes.
Then what you have to do is you have to model the 220 kV side like something like this.
Yeah.
So this model you have to model in the 400 kV side also. and then you have to study both the TRV. Like you have to place this TRV module in this breaker and also in the 220 kV breaker. So this is
Yeah, so
fault
you need to check for both breakers.
yes,
Transformer.
exactly. Yeah. So transformer breaker. So this is one case which is fault on 400 kV side. Similarly, there should be a fault at 220 kV side, and you have to measure the TRV at 400 kV side and also 220 kV side.
Now a small question on this. While we are creating this cable line fault or this particular fault, any well fault majorly in the substation, what breakers and are we going to keep them turned on like in
Okay.
we
So
were
for
doing in
example,
different way, switching,
if
sorry.
okay, done. If there is a fault here, if there is a fault, like I'm going to take three cases. Like for this, I'm going to take three cases, which is fault at the terminal of the breaker, and
Yes.
fault at the short line, and fault at the remote end, right?
Yes.
So this breaker should close, right?
Yes. Then only it will.
And this breaker should close. And if it has a 220 kV side, like that breaker, if so, the basic thing is you have to close this breaker, and the time should be same. Like that is important. For example, like I'm going to close this breaker, this at the fault is 0.3, and I'm going to close at this breaker at 0.4. The same time I have to close this breaker also. Just give me one just a minute. I'll take one of the case and I'll show you
Okay.
how we done it. Just 1 minute. I'm just opening it. Just a minute.
No problem.
This is a reactor switching case 11. Case 5. So which is OHL. Yes. So can you see my screen now, Imanshu?
Yes. Yes.
So this is one of the cases which is short line fault on the cable.
Yes.
So look at the breakers which I'm going to open. So this breaker I'm going to open, and the time is REM rec, which is from the transmitter. Because from one module to another module, we have to use something like this.
Why you
So
are going to open, close this? Say again. So this is sending the fault. It should be closed always, isn't it?
yeah, this is all normally closed. This is a source.
Yes.
And I'm going to close at particular time.
You mean open?
I'm sorry. Yeah, open. I'm so sorry. Yeah, open.
That's what I thought. Yes.
Sorry. That's open. Yeah, like I'm going to open at the particular time. The same time I would have given. This is the breaker I'm going to measure.
TRV. Yes.
That's the same time I will be giving here also. Like see, the same time.
Yes.
That is the same time. The same time.
Yes.
So that should be same time.
Yes. So when you open this breaker, same time you open that breaker, right?
Yeah,
That
yeah,
what you mean?
both of them. Like the fault is at 0.3 seconds, let us assume. The breakers are going to open at 0.4.
Yes, both of them.
Yeah, both of them.
Yes.
So
Okay.
this breaker is my this is in my GIS. Like this breaker is my objective. I have to study the TRV near. So that's
Yes.
why,
Yes.
and that's why I have included the TRV model here, and I have studied it.
And what do you do with the other breaker on this same bay but towards this 220 kV side? Then you also
Here,
disconnect that.
yeah, here I have measured the voltage. Here also I'm just closing it, like you can see, right? The same time
Yes.
I'm closing it. I'm
Yes.
sorry, like it's opening it. Yeah, same time I'm opening it, but I have measured the fault current here and here. Only on this
Yes.
breaker the fault current is higher. So I just
Okay.
took this worst case and I have done it.
Yes.
So that's why
And
I have included the
then
TRV.
what about the sorry to interrupt. And then what
No, no,
about the other two incomer? So say there is another cable coming in, so you leave them whatever they are.
just
Okay.
zero, like that's it.
Okay.
So because I'm going to study this cable, like this cable, there's a fault.
The other feeder doesn't really matter in that case, is
Yeah,
that right?
yeah, doesn't matter.
Yes.
So
Okay, that's what my question was. Yes, I get it now.
yeah, fine. So short line fault, remote end fault, and terminal fault are over. Like this is how you have to define some cases, and this is how you have to do it. I'll send
Okay.
you the model.
Yeah.
Like
Yes,
just at
please.
least
That
just
would be
try to
great.
understand the model how it is, and if you have any doubt, like we can discuss. That's not an issue.
Hello.
Hello, am I audible, Imanchu?
Yes, yes, I can hear you now. Yeah.
Yeah.
I think there was some issue in my internet or your internet.
Fine.
Yes.
Okay. So I'll just send you this model. Like you can use that model. Like just try to understand what is in that model.
Yes, and if that's not your license copy of that standard, can you give me that as well? IEC 622 something. This IEEE I have, but not the IEC. The one tells you the breaker calculations.
Yeah, yeah.
Yeah. Yeah, Gokul, you can send it to him personally.
Okay, sir. Like okay, fine. I'll send it. I'll send it.
Yeah.
Fine.
Okay.
Okay.
Yes, I will go through the model and I will check it. I understood everything is fine, and but I will try to memorize it, like how this is exactly happening.
Fine. Okay. Okay, much. Okay. Then so this is all about TRV.
Okay.
So yeah.
So next week we again come back on Friday.
Yes.